Okay, then we'll go from current slide. Now we're going to back up a little bit from this and do something else first. But let me go with this. So if you go to this course in Blackboard, homepage in Blackboard, there'll be, and they've gone to a newer Blackboard this time, and it's a lot fancier and maybe almost sillier. Instead of, in the old Blackboard, there was a tab over here, a blue tab that said content, and I put everything in content. Now they have just a page and a half of blue tabs, and one of them says my syllabus, so that's where I put the syllabus, okay? So you can go see the syllabus in static form and read it and all like this. And by the way, I have updated it since we met last time, because last time I didn't know what my office hours would be or anything else like this, so I'll go over the changes that I did make in those. And it may, and I'm pretty sure it was also the case that the syllabus I went over last time was the last fall syllabus, which the bulk of the course is the same, but the dates and times are different. But also, the format of the syllabus was different because I came up with a new format in the spring, and last fall we were on the old format. So it'll look different from what you see if you look at the YouTube video. But it'll be basically the same material. There's a lot more stuff they've added, just like they added more to Blackboard. Okay. So the syllabus has been updated. There may be one other little change I'll make, or I'll at least tell you what that change is, and then we'll go from there. Okay. So there's the syllabus. Then somewhere other on my computer, usually it's right near the bottom of that first screen, but it depends on what size screen you have. It may be on the next screen. But there's just a bunch of blue tabs here. And look for one that says class handouts and more, or something like that. It's sort of a strange thing to name it. It's not really class handouts. It used to just be content. Content made sense. Now it says class handout and more. And in that, I put all the rest of it. And here are some of the things that are in that. The research paper general instructions, okay? And again, that's in static form. I keep saying that. I'll come back to why I say that later. There will also be my locator card, and this is where the change comes from last time. Last time we met, I was not sure if one of my morning classes was going to May. They've allowed both of them to May. So basically that means my Tuesdays and Thursdays are probably just as bad as I was telling you last time. I have an 8 o'clock class that goes to 9:50, a big 10-minute break. Well, I usually come in about 7:45. This morning I was there earlier. Most times I try to get here a little before 7:45. So I have from 7:45 to 8 o'clock on Tuesday and Thursday. Okay, that's not very long. Just getting ready for the first class, basically. And my first class is 8 to 9:50, and I have a big 10-minute break to swap out books and stuff and grab, maybe today it was string cheese. Okay, just a little something to eat in that 10 minutes and get back up here for my 10 to 11:50 class. And then I had another big 10 minutes between that one and this one, and I ran down to my office, swapped out books, and ate pieces of stick cheese again. Okay. And then this class goes from, as you were asking, 12 to 1:50. Technically, that's the lecture part, and then we have a 10-minute set up the lab if we're going to do a lab, and then the second part is 2 to 3:30, technically the lab part. And as I told, yes. Okay, so pretty much, yeah. I'll talk about that in a minute too. So, but I'm real flexible, and that's addressing your question there, sort of. I can remember when I was in physics class, when I was an undergraduate, my sophomore year, quite often we go into a physics lab and have lab on something we hadn't covered in class yet. And I was totally lost because I didn't know what they were talking about, why we were doing it. None of it made sense. We were just doing whatever they said to do with no it wasn't adding to my learning at all. The next day in class, we'd have something that we talk about it and say, oh, that should have been what I was getting out of this, but of course it was all over. I couldn't remember what we had done. So I like to always make sure we covered the material before we do the lab, because otherwise I think it probably makes no sense to you. Okay, now, the next issue is most of the labs are designed to be 2-hour labs, because that's what they are fall and spring. And so that makes them 3 hours lab in the summer, but that's a wasted hour because they're designed to be 2-hour labs. So I split it up and make it an hour and a half each day so that one day we'll be doing lecture. So I always allow at least 2 hours for lab. Now, if we were to finish the chapter, which I don't think we're going to do today, if we were to finish this chapter and have 2 hours left, in other words, backing off from 3:30, finish it by 1:30, then we would do a lab today. Let's start at 1:30, not at 2, okay? Since I doubt if we're going to get that far today, we'll just go straight through. We may finish chapter 1, we'll go and get started on chapter 2, but then Thursday, we'll only do an hour and a half and then do the lab. Well, actually, we may actually have less than that. Yes?
Are there any assignments that you assign us?
Okay, I'll talk about that in a minute, too. Not specifically, but we'll talk about it, okay? Now, let me get your name before I forget. Miss Pink. Kayla, okay. And you go by Kayla, right?
Yes.
Okay, all right. Good deal. We're just reviewing some of the stuff from last time because we have 2 new students this time. So, that's, I can't remember how we got off on that. But the next thing in here was, I was talking about my schedule. So we have the class and lab today ends at 3:30. It looks like on paper that I have 30-minute office hours. But the bad news is my next class is on the Birmingham East Campus, which means it takes me almost 30 minutes to get there. So I have to leave here just as soon as that 3:30 rolls around, swap out books, get everything I need, and head to Birmingham. So that 30 minutes is spent mostly driving, not being in my office, okay? And then I have that class from 4 to 5:30. It doesn't have a lab. And here's the new addition that I didn't have last week. I will have office hours from 5:30 to 6. But the bad news is they're going to be on the Birmingham East Campus because I'm not going to drive back here. Otherwise, they were going to be office hours driving again. Then I turn around and drive home. So it'll be on the Birmingham campus. The East Campus is Ethel Hall. There's the Ethel Hall building on this campus. There's the Ethel Hall building on the East Campus. There's the Ethel Hall nursing building over there. I'm on the first floor in room K103. It's real close to the entrance when you come in. You come in and there's a hall this way or that way. Take this hall just past the restrooms is 103. So that's where I'll be for my next 30 minutes of office hours over there. I don't have that even in the new syllabus because it didn't dawn on me that I did have time I can have listed office hours there. Okay, so that's my locator card. Oh, that was the Tuesday, Thursday. Monday, Wednesday, here's where the changes occurred from what we were talking about last time. I thought I might lose one of my physics classes, but keep the other one. I wound up losing both of them because I had one small, Dr. Bryant had a big, so we were going to stack those together. But then I had one that made, I thought his did. His didn't make, so we're going to stack those two together, and he's going to teach both of them. So that gives me a bunch of office hours on Monday and Wednesday. Again, I have an 8 o'clock class in the morning. I come in about 7:45. I have an 8 o'clock class, but it's a calculus class, which is a 4-hour course. And in the summer, that means it's 8 to 10:40 is when it meets. Then I have 20 big minutes before my next calculus class, Cal 2, and that's 11 to 1:40. But then from 1:40 until 6 o'clock, I have office hours. I put on the thing 1:45 till 6 o'clock. On Mondays and Wednesdays, I have office hours that whole block of time there, which is when I'm going to get all the stuff done, hopefully, that I need to get done. Because the other times are too short to get anything done, except maybe that 30 minutes over on the Birmingham campus. Okay, so that's my schedule. Fridays. Okay? This is sort of strange. But Fridays, when we're on campus, I'm on the Birmingham West campus from 7:45 until 11:45. Okay? However, in the summer, we had Friday last Friday, and we'll have a Friday this Friday, okay, on campus. But starting the rest of June and the whole month of July, the college is closed on Fridays to save on energy because these are old buildings, they're hard to cool, and so they just decided to shut down. So we were working 4 10-hour days rather than 5 8-hour days. So I won't be on campus at all after this Friday. I know this Friday is the first of June, but the rest of June I will not be on campus in all of July. Now, right at the end of the term, August, the first Friday in August, I will be on campus again. But I put it on the thing, and let me get your name, please. Yeah, Jordan Tipton, got it. Okay. And so this Friday and the one in August, the only Friday in August, I'll be on campus 7:45 to 11:45, Birmingham West campus. Okay, so that's my locator card and my office hours. The next things that are on that fast handouts and more, whatever that silly tab is, I have all the PowerPoints for every chapter we're going to cover. By the way, that's chapter 14, 15, 16. That's astronomy. 17, 18, 19, and 20. That's earth sciences. We skipped 21 and 22. 23 is meteorology, weather and climate. And 24 is Earth's waters, which is oceanography. Okay? So those are the chapters that the PowerPoint should be out there. Now, that's not all that's out there. Sometime way back, many years ago, when I was teaching this course, one of my students found these 10 incredibly beautiful pictures that were taken by the Hubble Space Telescope. And he sent them to me, and they were just incredible. So I put those out there, okay? And it'll say Hubble 1 through Hubble 10. They're just 10 incredibly nice photographs. I think there's some narration with them, not narration, verbiage with it. But even if not, they're just incredible pictures. There's another one that's called Space Objects in Perspective. And this is either the same student or another student found this, and it's really interesting. It shows a fairly accurately scaled Earth with the moon, okay, much smaller, and with Mercury, Venus, and Mars scale. Of those first 4 planets, we are the largest, but just slightly larger than Venus, much larger than Mercury. In fact, Mercury and the moon are almost the same size, and then Mars is in between Mercury and Venus in size, okay? Then it shows the Earth scaled with Jupiter, Saturn, Uranus, and Neptune, the 4 big gas giants. Now the Earth seems really small compared to them. And then it shows the Earth compared to the Sun. And we're basically just like a pixel on the page compared to the Sun. Maybe a little bit bigger than that, but not much. And then it shows the comparison of the Sun to some other stars. Some that might be smaller and some that are enormously bigger. We've just got an average sun, okay? Our sun is an average star. So there's some that are just, it makes our sun look like a pixel on the page almost. Okay. Then it shows size of galaxies, and things, and boy, it just gets incredibly. So it's a really nice visual that goes along with what we're doing in this first chapter. So there's that one. There's the PowerPoints. Trying to think if there's anything else out there. I think that's most of it. Okay. Oh, and the one last one is the link to YouTube videos, which have the thing, and that's the one I was wanting to tell you about. So if you go to the website, go to Blackboard, the home page, go down to the My Syllabus, list of syllabus, and then class handouts and more list everything else. And if you go to the YouTube video link, click on that, then you'll see that video, click on the video, and you'll hear me talk about the syllabus, talk about the research paper instructions. So this way, I said before, you got them static form, now you got them dynamic. You'll hear me talking about what's expected, this kind of stuff. Okay? And then also, we did in the last class, didn't we talk about safety? We did, didn't we? I think so, yeah. Okay, so we hit safety. So especially for that, you need to listen to it. Okay? Then, next. Then we got started in chapter 14. Okay? So this is where we left off. This is only slide 7. So we didn't get all that far. But before we get to this slide, I didn't realize it until we had passed it. On page 356, for those who do have a book, now the little books, there may be 2 different page numbers in it. One, the page in that book, and then the other is the page from the original book. See, that is a customized book taken out of this book. It left off chapters 1 through 13 and just did starting with 14. So see what your page numbers are in there. It should be the very first chapter you have. Okay, and it doesn't have another page on there, page number? Okay, yeah. That's the one I'll be referring to, is the 350 something. Lauren, right? Under the bed. Okay, got it.
Do we need to purchase the bigger book, or is this okay?
Say again?
Do we need to purchase the bigger book as well?
No. That has everything the big book does, or just about everything. It's just a lot cheaper. So, and that's what the bookstore has, right?
Yes.
Yeah. You can get other editions. Which you have, the big one or the little one? You have the little one too. Okay. If you find used big book, that may be as cheap or almost as cheap as this one, especially if you're going to do both 111 and 112. You don't have to, but if you did choose that. Let me get Lauren marked here before I forget. Okay. I'm sorry? A digital book is fine. E-books are fine. And I believe they have that. This company, I'm pretty sure, does. Okay. So, does that cover most of what we need to catch you up? You can go back and see and hear everything that we did through that. So for the rest of you, I do have everything out there now. The only possible thing is I have it on the locator card, those hours at the end of Tuesday and Thursday. I just didn't put it on the office hours on the syllabus like that. I'll probably go back and change that, but right now you won't see that. But I didn't think about that until too late. Okay, before we pick up where we left off last time, well, we have somebody else. Let's see. Name is it Pius? Yeah, okay. All right. We're missing Guy. We're missing Justin. And we're missing Jacory. Other than that, almost got a full house. Okay. So, didn't cover the example 1 on page 356. And one of the reasons this is kind of a made up, it's a true problem, but I don't see, it's just having you manipulate numbers just for the sake of manipulating them. But it's still a pretty interesting thing. The Orion Nebula, now for those who weren't here, and even those who were here, what a nebula is just a mass of stars, a mass of gases, just an enormous mass of gases, occupying an enormous volume of space, just gases, just floating around out there. You think of space as being a vacuum. It's not quite. There's stuff out there. But this is sort of a collection of gases that's a little more than a vacuum, but it's a mass of gases. Is about 20 light years across. Remember what a light year was? It's not a time measurement, it's a distance measurement. It's how far light travels in a year. And we went through the calculation, not exactly, but pretty close, 186,000 miles per second is the speed of light. Multiply that by 60 and you have more than a million, more than a million, in fact 7 or 8 million miles per minute. Multiply that by 60 and now you're up to tens or hundreds of million miles per hour, and multiply that by 24, now you're enormous number. That's how far it travels in a day. Multiply that by 365 or 365 and a quarter or something like that, and you have how far light travels in a year, which is a long, 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 long distance. Multiply that by 20, and you have how big the Orion Nebula is. That's its diameter. And it's roughly a spherical area with a volume, and they give it here. And why they give it to you in cubic centimeters, I don't know, okay? And they give you the diameter in centimeters, which is crazy. They should at least be using meters. Okay, and it says calculate the approximate number of hydrogen atoms in the nebula, okay? Then determine the number of sun-like stars that might be formed in such a nebula. Okay? Now, they give you how big it is and with the volume, but they don't tell you. I'm trying to see if they say it anywhere else. I just don't see where they get the, okay. They say they just give it to you here, about 1,000 atoms per cubic centimeter. Now that wasn't given in the problem anywhere I can see, but they just throw it out there. That's like I said, this is kind of a made-up problem. Multiply that by how many cubic centimeters, and that tells you about how many atoms, and it is an enormously large number of atoms. Okay? It contains about that many atoms. A star like our sun is formed by approximately, and then again, they make up a number. And I mean, it's a true number, but it wasn't given to you in the problem. And then it says how many stars the size of our sun could you get, and that's about 4,000. 4,000 suns could be made out of that huge nebula out there. Now, it probably won't, okay? The odds are you're not going to form that many stars. You're going to maybe form one or two sometime or another, maybe a few, and then the rest of the gases will get blown out somewhere else to make up other stars. Thus, there is sufficient number of hydrogen atoms in the Orion Nebula to produce about 4,000 average stars like the sun. That's the point of what they were saying. Having you do the calculations are fine, especially if you like math. They're sort of fun to do, but don't expect a question like that on a test. I'll put it that way. Okay, so let's go back to where we stopped last time. Last time we were talking about stellar modeling. This is how most stars, in fact I would say all stars, are formed. Okay, at the very center of the star. By the way, the star is a huge mass of very hot, very, very hot gases. In the core is the hottest, the densest region of the star. It's the only place that nuclear fusion happens, is in the core, okay? And it's going on there big time. That's why it's so hot, because nuclear fusion releases enormous, I mean incredibly enormous amounts of energy. You take Nagasaki, Hiroshima, and probably add them together and multiply by 2 or 3, and that's what one fusion bomb would be. This is like millions or billions of fusion bombs going off at the same time. Incredibly hot, incredibly dense region. That's where the fusion is happening. And it's releasing deadly gamma radiation, X radiation, just all sorts of really mean and nasty stuff. And it's radiating outward. And this is where we left off last time. You next get to the radiation zone. Now, for those who weren't here, this may be a little new, but for those who were here, hopefully you'll remember this. Remember, this star, before it was a star, it was a nebula. But then something perturbed it, and you started having what they call gravitational collapse. You had some sort of shock wave come through or something that pushed some of the atoms closer together. As they got closer together, they stuck together, and then they started attracting other atoms of gases until it built up, and all the time getting more and more pressure, more and more weight, and more pressure, more and more heat. And finally you got so, at that point it became a protostar. That was what was going to become a star, okay? Before it was just a mass of gases. And the protostar, when it got hot enough to start fusion. So all before this, you have collapse. The gravitational pulling the atoms closer and closer and closer together. That's called gravitational collapse. When that core got hot enough from the friction of those molecules bumping in, and atoms bumping in and rubbing against each other, and that's incredibly hot, then you had fusion happen. Fusion starts pushing outward. So gravitational attraction is pulling inward, fusion is expanding greatly, and that's then called the radiation zone. Around that is where the outward force of the fusion reaction is pushing out. The radiation diffuses outward now over millions of years. Okay? Now, that's not all within, well, it's happening over millions of years, but it's not taking that long for it to diffuse outward. Okay? Because radiation moves at almost the speed of light. So that's a little confusing here, but that's happening in the radiation zone. Then you get near the edge of the star, okay, and now things are beginning to cool off. Out here, they certainly are cooling as they move outward, but now you have a boundary out here which is basically close to absolute zero in temperature. This is incredibly hot in here, and you have that mixture, and this is called the convection zone. In the convection zone, the hot gases are moving out, but they're cooling off and collapsing back. So you have, this is what sort of defines the shape of the star as a ball of gases, because you have this convection moving going on. Now, I don't know if you remember if any of your moms or grandmoms had that a special kind of cookware they called visionware. It was really glass pots and pans that you could see through, sort of an amber color that you could see through. And if you find any of that, boil some water in that, and you'll see convection going on in the water. You can sometimes look at the top of the pot and kind of visualize this. You can see it from the sides on that. But that's what convection is. Hot gases move upward, the cooler gases move downward, and you have this convection going on all around the star. Okay? Now, not getting into this now, but some of this convection, what have we got going on outside right now? All that rain. Where did it come from?
Clouds.
Say again?
Clouds.
Clouds, okay. But what was the system? Is this guy? Okay, I thought so. All right, anyone else come in and since I called roll? Okay. What it came from was a tropical depression. Did it actually become a tropical storm? Alfredo? I think it became a storm. It's not now, it's a depression again. But it actually became a tropical storm. What a tropical storm is, convection region. Okay? Hot air is moving up, cooler air is coming down. And that happens because the sun spins, because the earth spins. You have turbulence there, and that's what creates hurricanes, tornadoes, tropical storms, all this kind of cyclones, all this kind of stuff. So guess what? You can have storms going on in this convection zone, and some of these storms on our sun are called, anyone want to hazard a guess? Sunspots. These are dark areas where the temperature is greatly different, I think usually cooler, and you have storms going on around there. So this just looks like a nice placid little ball here. There could be lots of storms happening there. And if you see pictures of the sun, you'll see solar flares that just go out into space. So yeah, lots of things could be going on in that radiation zone. So the radiation zone is inside. The convection zone, structured by hot material rising from the interior, cooling and sinking. In that process, with the spinning of the star, then creates storms. Okay. The upper reaches are the visible surface of the star, but it's not a solid surface, it's a gas. The sun, our sun, an average star, our surface temperature of the sun is 5,800 K. Now remember what K is? Second? Okay, no, this K doesn't mean, this is capital K. The little k means 1,000. This is Kelvin. Okay, Kelvin is absolute temperature. This is how many Kelvin there are above absolute zero. Okay, that's a lot, folks. That is an incredibly hot surface. The core, probably millions of K. Okay, the surface is 5,800. Big, let's see, hot stars, really hot stars, which are usually pretty big too, probably are 10 or 15 times hotter than that on the surface. Some big stars are quite cool on the surface, would be maybe half that, and then there's others that are in anything in between. Okay? So that's our three zones of a star. The core is where the fusion happens, radiation going on in between the core and the surface, and the convection zone is right around the surface. Now, this is all hitting it pretty hot and heavy, fast. Reading the chapter, I'll say this every time, nothing replaces reading the chapter. Preferably before I go over it, that way what you've read will start making more sense. But even afterwards, hopefully what I'm saying will start making more sense once you read. I think it's usually better to hit it early. Okay? So there is how most stars are set up. In fact, all stars. Now, let's talk about the lifetime. And this may be something that may seem counterintuitive. Okay? Our sun, the star that provides us our energy, converts about 1.4 times 10 to the 17th kilograms of matter. Now, 1 times 10 to the third is called 1 megagram, which is 1 metric ton. So this is 1 with 14 zeros following it, times bigger than a ton. So this is a lot of material, okay? It converts that to energy each year. Now, what is meant by that? How can you convert matter to energy? Does anyone know? Fairly famous formula that all of you know, but whether you realize it pertains here, I don't know. If I give the name of the person who came up with the formula, you'll probably get it. Einstein. What was his? Say again? What? That's it. Let me get my pen set up. E is equal to mc squared. Okay? Now, anyone know what m stands for? Mass. Okay? Here's a mass unit. Okay? 1.4 times 10 to the 17th kilogram. Enormous, enormous amount of mass. Multiply that by c squared. What is c? Does anyone know? I've already mentioned it today once, but I didn't call it c then. It's the speed of light. Remember how fast the speed of light was? 186,000 miles per second. Of course, in order to use this formula properly, you would need to change that to meters per second, which would be, goodness gracious, a incredibly large number. Justin's here. Now, folks, we are all but Jacori. All right, great attendance, folks. Keep it up. Okay, so if you can imagine, let's just go back to 1 kilogram times something far bigger than 186,000 squared. That would be something of about 12 zeros behind it, okay? A number with 12 zeros behind it times 1, that would be how much energy? 1 kilogram. Multiply that by 10 to the 17th, and you've got an enormous amount of energy going on. Okay? Which means, though, that the sun is losing mass constantly. That's about 2,700 3-ton SUVs a year. Okay? Each year is losing that much mass. So guess what? It's not going to last forever. Okay? But that's not really the big limiting factor. We'll talk about this in a thing. We think our sun was born from some nebulous about 5 billion years ago. Okay? What's going to make the determination is not how much mass it loses through its energy that it's giving off, but how much hydrogen it has. Because the hydrogen fuses to helium. Okay? When all the hydrogen's used up, helium will fuse to carbon, but that takes off much more energy. That is much hotter circumstance, and I don't know if our sun's going to be hot enough to do that. But guess what? We're going to be long dead before that because we would have used up that, and then we'll go into later what's going to go on there. It's incredible. We will not survive it, I'll put it that way. But we've got enough hydrogen for another 5 billion years. So it'll last for your lifetime anyway. Well past. In fact, I doubt if we'll be around. We'll wipe ourselves out before that. But anyway, another 5 billion years. So our sun has a lifetime of about 10 billion years. That's average. Now, lifetime depends on the stellar mass. You tell me, bigger stars live longer or smaller stars live longer? What would make sense? What's that? Not going to make a guess, huh?
I would think smaller stars.
Live longer?
Because they don't take that much.
Because what? You would think bigger stars would live longer. But you're right. The smaller ones have the longer lifetimes. Why? Because they burn I say burn, they fuse their materials much faster. They're incredibly hotter, so they are fusing like crazy. So the less massive stars actually live to be trillions of years old, and the most massive stars only have a few million years of life, not billions like our sun. So actually it's sort of reversed. You would think, well, they have more mass, so they'll last longer. No, they don't. They're burning it faster than, so much faster. Now, I say burning, that's not really the right word, but that's what the astronomers use too. I just got used to saying it. It's really fusing much faster. Okay. So the more massive stars have shorter lifetimes, less massive stars have longer lifetimes. So we're right in the middle. Now we pick up with brightness of stars, which is on page 358. So what's the brightest star that we see? The sun, okay? You don't see any other stars out there right now because the sun's light just completely swamps them out. Now when the sun's on the other side of the earth, we see the other stars, but they're really minor compared to the sun. Was that because the sun's that much brighter than they are? The sun's that much closer than they are. In fact, the sun is only 93 million miles away, and they are gazillions of miles away. So that's what makes the relative brightness. Okay? So what are the differences in stellar brightness? Well, 1 is the amount of light produced by a star. In other words, how fast is it fusing the materials, hydrogen or whatever it's doing. Another is the size of a star. If a star is quite big, it's easier to see and it's brighter. If it's quite small, even though it may be much hotter, it's harder to see. Okay, so the size of the star matters too. But the biggest thing for us is the distance to the star, because close by stars appear brighter, even though they may be smaller and less light being produced. But if they're much closer, they're much brighter. Okay, whereas very, 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 very distant stars may be huge stars producing an awful lot of light, but they're so far away you can't detect them as easily. So this adds up to what we call apparent magnitude. What does it look like to us? There is a scheme that's been used to quantify this observed brightness, and you just take the sun completely out of it because it would wipe out everything. The first magnitude star is 100 times brighter than the sixth magnitude star. This is leaving off the sun altogether. The first magnitude would be 100 times brighter than the sixth magnitude. 5 uniform divisions in between that, and you just split it down by like 20 times, 30 times, 20 times, 40 times, 60 times, 80 times, that kind of stuff. So 5 uniform divisions in between the sixth magnitude, which you barely can see, and the first magnitude, which is the brightest star we can see other than the sun. Okay? And here's a table. This is also in your book. And here's what we've got going on here. Here is 0, which is the brightest star out there. Sirius. Brightest star in the sky. Are you serious? Yes, we are. Now, does that mean it's the hottest star? The biggest star? No, not necessarily. It's a combination of all these. This is, but it's also big, and it's also producing a lot of light. Okay? But it's a distance away. Now, the dimmest star we can see out there, it's the naked eye limit with large telescope. Oh, wait a minute. No. Farthest star that can be seen with the naked eye, this is 6. So there's 100 times difference between 0 and 6. Okay? But if you have binoculars, you can go up to 10. And if you have a very large telescope, you can almost get to plus 20. Okay? Now, to me, I don't know why they did this. The apparent magnitude, which is what we're talking about, apparent brightness, okay? They make the dimmest stars pluses and the brightest things minus. I don't know why. It seems totally backward to me, but there must be a reason. Now, Sirius is the brightest star out there, but quite often Jupiter, when it's a full Jupiter, meaning on the opposite side of the sun, is brighter than Sirius. And it's maybe a 1 or a 2 here. The brightest Venus, which is the brightest object we see outside the moon and the sun, that's up here around, what, 3, maybe. So Venus will be the first star you see. It's not a star. The first thing you see in the evening or the last thing you see in the morning. And therefore, it's called the morning star or the evening star, but that's Venus. Now, you may not see it at all because it may not be on the other side of the sun or something, and you can't see it. So the odds are, if it's not Venus, it's probably Jupiter then. But if neither one of them are visible, then it would be Sirius. And you can't always see Sirius. Look at where the full moon is. That's about 12, minus 12. And the sun, minus 26. Okay. Completely wipes out everything else. Okay. If the sun is out, you don't see anything else out there because it blanches it all out. But what they're talking about here is between the brightest star and the dimmest one you can see, 6 uniform divisions, well, 0 to 6, and it's 5 uniform divisions. Okay. Now, that was, okay. that was apparent magnitude. That's what it looks like to us. When we start dealing with the actual stars themselves, we want to know absolutely what the magnitude is, not what's close or whatever. This is the brightness adjusted to a defined standard distance. In other words, if we took all the stars out there and put them the same distance away, what would be the magnitude then? Guess what? Our sun would be right in the middle. Not very bright, but not too dim. Okay? So it's the brightness adjusted to a defined standard distance. For example, our sun, the apparent magnitude, like I said, minus 26, almost minus 27, minus 26.7. Absolute magnitude plus 4.8. Okay, on the downside. Okay. And lots of the other stars would go to be closer to 0. It might be very low to 4. Okay, so it's all over the place. Now, another concept, luminosity. Total energy radiated into space per second. Okay? I would just say per time period. Okay? Directly related to the absolute magnitude. The bigger, the brighter the stars, the greater the total energy is going out there. So units correlated to the sun. If the sun is called 1 solar luminosity, the much bigger stars would be far larger than 1, and the smaller stars would be less than 1. Okay? So that's luminosity. We're really not going to do too much with that. We're going to deal a lot with absolute magnitude, though. Now, before we get to star temperature, they have a couple more examples here, and again, they're kind of made-up examples. The brightest star in the Earth's night sky, what did we say it was? Sirius, okay. Now, it's not spelled like "Are you serious?" It's S-I-R-I-U-S. Absolute magnitude of 1.4, which tells us that Sirius gives off more light than our sun because our sun is 4.8. Remember, the smaller the number, the brighter the star. Okay? So, apparent magnitude of Sirius was 0, if you remember. The absolute magnitude was 1.4. Okay? So it says, how many times brighter is Sirius than our sun? Okay? Well, we said, if you go back to this slide, the first magnitude star is 100 times brighter than the 6th magnitude star. Okay? So there is the range from 1 to 6. We're going from 1.4 to 4.8. Okay? So that would be 3.4. Okay? Would be the difference in our absolute magnitudes. So that would be a little bit more than 50. I'd say probably close to 60. Whoa, no, they say 23. Sorry, it's a log scale. I was not doing log scale. But again, this is not something you would expect to have on the test, so don't sweat it, okay? But just to give you an idea. So Sirius would be about 23 times brighter than our sun. A very bright star, hot star. Now here's example 14.3. Star A and star B are the same distance from Earth. Star A has a magnitude of -1 and is 100 times brighter than star B. What is the absolute magnitude of star B? Okay. Well, remember they said there's 5 even divisions between these for 100 times the brightness. So between 100 times would be 5 differentiations. If one's at -1, that's the brighter one. The dimmer one would be a +4. Again, 5 divisions. Don't sweat that. This is just so you can get a grasp of some of the concepts there. Okay. Let's move to star temperature. I've already given away part of this. but not all of it. How can you look out there at a star and tell its temperature? You kind of would think no way you can do that. You don't know how far the star away is, you know, that kind of stuff. But really, there is a way, by the color. Now, would you think red would be hot? Red is the coolest star. Blue is the hottest star. And think about this. All of you built a campfire or a fireplace or something like that, and the flames in there are mostly what color? Red and yellow and orange kind of thing. But on your stove, if you have gas heating, what is your stove? What flame color is that? Blue. And believe me, that's a hotter flame than you get in your fireplace. Okay? So, just like it with the stars. The red stars are your coolest stars, and your not cool as in Joe cool, but yeah, you know. Okay? The bluish stars are the hottest. Okay? So, on the night sky, though, can you see blue very well? That's an interesting question. I don't know. The whitest star and bluish tints, or more bluish tint, the hotter they are. The color is related to the surface temperature. Remember, that's way cooler than the core temperatures. But that's what we're dealing with, surface temperature. Now, they jump into something here they assume you know something about, because this was in chapters 13, 12, and back there. Of course, we're starting in 14, so you don't necessarily know anything about it. Black body radiation curves. Let me just sort of show you what that's talking about. These are called black body radiation curves. Now, these are the wavelengths given off of these so-called black bodies. Bodies out there, they're not necessarily black, but they're just bodies out there at different temperatures. They're giving off a variety of wavelengths, okay? Some very short wavelengths and some extremely long wavelengths. The shorter the wavelength, because wavelength is inversely proportional to frequency, again, you don't necessarily know this, but I'm just telling you, the higher the frequency, the more energy is given off. So the shorter the wavelength, the higher the energy. The longer the wavelength, the lower the energy. Okay? So, there are some stars out there that are very, and this is relatively short wavelength, by the way. These are angstroms, which are a unit that's not used that much anymore, but it's a very, very small unit, like 10 to the minus 8 meters or something like that. Okay? So these are very high energy, low wavelength energies given off. And the objects out there, these could be stars or whatever it is, around 3,000 K. Remember, our sun is 4,800, was it? Okay, surface temperature. A couple slides ago. 4.8, right. Okay. So that's something around here, and guess where we are? A good old yellow star. That's what color our sun seems to be, yellow. Okay. But those that are down around 3,000 K, those are your reddish stars. Okay. Red giants. We'll talk about those a little bit later. The bluish are up here 10,000 K. Those are the hottest stars. Which of these are going to live longer? The smallest. The low temperature. Yeah. Exactly. They're not burning, fusing as much of their fuel. Okay. It takes a lot of fuel to maintain that thing. Okay. Now, they give the whole spectrum here. Up here is not the whole spectrum. Here's ultraviolet light. What do you know about UV light, ultraviolet light? Good, bad, or indifferent? Second? In laboratory? What do you use it for? Okay, actually X-rays are beyond that. They're even shorter wavelength. They're up here. Are they good to have or bad? Bad, because they can destroy tissue. And ultraviolet light can too. It has fairly high energy. Where do you see UV advertised? I can think of two things that use UV in their advertising. Second? Sunglasses are number one, okay? Sunglasses, they block the ultraviolet radiation. Now, we have an atmosphere over us. Remember, we said way back here that the radiation coming out of here is deadly radiation, gamma and X radiation. It can kill you in large enough doses. Remember it was in the news not too long ago, maybe months or years, about a Russian former spy living in the United Kingdom who someone slipped him a Mickey that had high radioactivity stuff in it. He died. I think he died. And his daughter lived or something. But I mean, this stuff will kill you. I mean, we used the atomic bombs on Hiroshima and Nagasaki and killed hundreds of thousands of people. Not from the bomb blast. Most of those died from the radiation poisoning later. Long, slow, miserable death. Okay, this stuff will kill you. Well, the sun's putting that out really vigorously. Okay, remember that much mass times that much things, an enormous amount of energy, and that's out there in space. Well, guess what? What keeps that from killing us? Okay, our atmosphere, our entire atmosphere. Ozone's important, the ionosphere is important. Our atmosphere blocks most of that deadly stuff. Hardly any gamma radiation makes its way to Earth. Hardly any of the X-rays. A little bit, but not much. But right down, that's way out here. The ultraviolet, little bits of that do get through. Okay? And that's why your sunglasses, why do you wear sunglasses and UV protection? What's it protecting you against? Say again? Okay? And the damage it can do. I've had one cataract removed already. Cataract is when your lens in your eye gets cloudy because of radiation, ultraviolet radiation. And that's why sunglasses. If you just have dark glasses, but they don't protect you from the UV radiation, it's not going to help you with cataracts later. Okay? So I wear sunglasses anytime I'm outside now. This one's forming. They can deal with it now, but in third world countries, that's where a lot of blindness comes from. There's other reasons too, but yeah, it's there. Now, what's the other thing that you see advertised in UV? Ultraviolet protection, UV protection. UVA and B. It has to do with sun. Sunscreen, exactly. Sunblock, exactly. And the higher the SPF number, the more sun protection. That's what that stands for, sun protection formula, SPF. What's the result of that? UV hitting your skin. Second? Yeah, sunburn, that's exactly. You're killing tissue. And that's dead tissue that you're having to deal with. Okay? Now, some of you have a bit more beta carotene than some of the rest of us do. You're lucky because you tend not to burn as much. But some of us burn pretty easily. So the red hair, really easy, right? Okay, now, what's the result of that? Yeah, sunburn hurts and stuff, that kind of stuff. But prolonged over and over exposure to too much skin cancers, you got it exactly. I've already had one basal cell skin cancer removed. The spot on my nose right here is precancerous. I put sunblock on it every day, even rainy days, even winter days. Sunblock every day, just prolong the time before it does change to, because the more it gets exposed to it, the more rapidly it'll become skin cancer. Okay? But not just that. You know, some people were sun worshipers, out there in the sun every chance they got all summer long, as much as possible. They had these great tans. You know what they are today? Prunes. No, close to it. The more wrinkled, because guess what? You destroy elasticity and things like that in your skin. That's caused by too much exposure to sun. Okay? So, ultraviolet is not quite deadly. Now, some of the cancers, those can be. I have a brother-in-law who's already had one or two. Boy, what are the bad ones? There's basal cell one that starts with sarcosis or something like that. Then the other is melanomas. I had a neighbor back on the farm in Georgia where I grew up. She's died of melanoma. My brother-in-law, they caught both of his very, very early, so I think he's okay, but it can be deadly. Okay? Now, then you have the visible spectrum, and this is mostly what our atmosphere allows through. A very narrow wave band. All these get blocked pretty much by our atmosphere. Here is what comes through, the visible light spectrum. And if you have a prism, you'll see this. A rainbow, you'll see this. Red, orange, yellow, green, blue, indigo, and violet. Not quite broken down this way, but that's what it is. These are the high energy, hotter, low energy, cooler. Okay? And then down here we have infrared, which is sort of bizarre because that's what heat is. Okay? Wait a minute, I thought the hot, well, infrared is heat, well, basically heat energy. But what happens, now today it's not going to happen very much. But most days in the summertime, especially if it's not calling for any rain, do y'all drive in or do you have some other means of transportation? Any of you drive? You leave your, on a hot, sunny day, whether it's a hot day or not, a sunny day, no chance of rain. You ever crack your windows? Okay. Yeah, I do. I did today, of course, it's raining. But boy, I hate getting in because what if you go out there, you start sitting in the sun for a long period of time, open the door, it's 10, 15, 20 degrees hotter in the car than it is outside. Why? Okay, why is that? Because the visible light, any of this visible light, can go through glass. But when it goes through glass, it loses a little bit of energy and becomes infrared radiation, which is heat radiation. Then that doesn't have enough energy to come back through the glass. So therefore, it's trapped in there. And that's why we call that a special effect. What's that? It's what? It's heat. And there's a name for that process. People who grow plants use it. You know what?
When you dry the food out, can't think of the name of the word. When they dry the food out.
No, they're growing plants and keep them alive in the wintertime. What do they put them in? A greenhouse. It's called the greenhouse effect. That's it exactly, because you have glass or polyethylene or some sort of surface there that lets the light in, but then the heat doesn't go back out. And that's why global warming, there are certain greenhouse gases that act the same way. In fact, our planet Earth is so far from the sun, we should be frozen. Okay? But we have this atmosphere that lets this visible light in, but then traps it in here. And that's what keeps us warm enough to have life. Okay? So they keep saying there's got to be other planets out there that support life. Well, that have potential to be supporting life, but you have to have exactly the right atmosphere and exactly the right distance and a lot of things exactly right to support life as we know it. And we may be one of relatively few. Now, scientists will claim there's probably thousands of potentially life-producing planets out there, but everything has to be just right. And we just happen to be far enough away that our atmosphere traps just enough heat to keep us right. But certain greenhouse gases, which are carbon dioxide, methane, and a few others, they actually are more, it's like you have a thicker thing and they trap more heat in, and that's why we have global warming going on. And it's not the only time in history we've had that. There was one time we got hit by this way before mankind was here, by an asteroid, I think it was, and it created an enormous amount of heat. And it took us, I think they figured hundreds of thousands of years to cool off of that. And that may have been what killed the dinosaurs, okay? There's lots of speculation on that. But anyway, that just gives you an idea of what's going on. Okay, so the color variations, the coolest stars on the red side, the hottest stars on the blue side. They're related to the temperature as these curves show. You see, the curve shows all the wavelengths here. The hotter stars, the peak is more toward the blue end. The cooler stars, the peak is more toward the red end. Okay? Red are the coolest stars, blue are the hottest stars. Yellow, halfway in between. There we are. Good old sun, 4,800. Okay. We were right in the middle. Average size, average heat, average lifetime, average everything, just about. Okay? So, what are the classifications? Based on temperature, hottest to coolest. Now, these are absolute temperatures of the stars. Where did they get these letters? I do not know. Okay, it's kind of crazy. O is the very hottest. B is next. A is next. F is next. And we're down here in the G's. Okay? And then the K's and then the M's. It makes no sense. I don't know who came up with these and why they have these letters. Again, you don't need to know this. Probably a nice thing to know that we're a G star. Okay? Probably the upper end of G, close to F. Okay, but you'll see these in a slide coming up in just a few minutes. All right, so here's the breakdown of this. Your O, the bluish color stars, look at that temperature. 30,000 to 80,000 K. We're down here at 4.8, okay? Those are incredibly hot. And what you have there, spectrum with ionized helium and hydrogen, little else. Now, what do we mean by ionized? Anyone know? Again, this is something they probably are assuming you had in the first half of the book, and of course you haven't had the first half of the book. What do we mean by ionized? What is an ion? Okay. Let's back off and say, what is an atom? An atom is a nucleus that has protons and neutrons in it, surrounded by electrons. Okay? The protons are positively charged, the neutrons have no charge, and the electrons have negative charge. So an atom is when you have the same number of protons as you do electrons. Neutral atom. Okay? What an ion is when either enough energy has been added to the atom that it either has thrown out an electron or picked up an electron. Okay? And that means it's now unbalanced charge. If it lost an electron, it's a positive charge. If it gained an electron, it's a negative charge. That's an ion. Positive charged ion, negative charged ion. Okay? And how did that happen? Energy. More energy was considered. Are there any ions in the room? Generally, we're basically fairly neutral. Except for those fluorescent tubes there. What you have there, if you've ever looked at the fluorescent lighting system, is a big object up there somewhere called a ballast. Basically what a ballast is a capacitor which stores an enormous amount of charge. And that gives a big potential difference between the ends of those tubes. Those palms that go out like that. And what you have then, that energy either rips off electrons or something else rips it off and gains the electron, and then the ions are flying back and forth in that tube. Those are ions. Ionized. That's your ionized gases. that actually is called the plasma. You have solids, liquids, gases, and then plasma. Plasma is ion. This is the highest energy stuff out there. At today's temperature, you better believe it's highest energy. Ionized hydrogen and helium, nothing else. No heavier metals, nothing else. Only the two lightest atoms, and they're not even atoms, they're ions. Okay? Then the Bs. The Bs are also bluish, 10 to 30,000 K. These the spectrum with neutral helium, none of it's ionized. So there is all the lightest gases, helium. Okay? Then we have the A, which is still hot, really, really hot, bluish, and this is 7,500 to 10,000 K. The spectrum with no helium, strongest in hydrogen, some magnesium and calcium, which are lightweight, and I can't adjust for why the chemistry comes out this way, but it does. Then the Fs are the white stars. These are still hot stars, but 6,000 to 7,500 K. The spectrum with ionized calcium, magnesium, neutral atoms of iron. So that's getting down to heavier atoms. And here where we live, G, our sun, yellow in color, 5,000 to 6,000 K. We're actually 4,600, so we really are orange red, but we're counted a G star. The spectrum shows 67 elements in our sun, okay? In the sun itself, okay? It's quite a few. Basically, between a half and 2/3 of the elements that exist. Then the K stars are the orange-red stars. In some senses, we really go on there because we're 4,800, but I think they usually around that 5,000. So, spectrum packed with lines of neutral metals, and then the M stars. These are the reddish stars. That doesn't seem cool to me, but 2,000 to 3,500 K. Band spectra of molecules, titanium oxide, other spectral types based on molecules. So not just atoms or ions, they actually have molecules now. So you don't need to know all that. Basically, that we're yellow, average, cool, average to cool. That's where our sun lives. All right, any questions on that? But the start temperature is important, okay, and we'll see why in a minute. This is why we've been talking about these things. You might say, blah, 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 why did he bring all this up? This is why. By the way, paper topic-wise, here's a couple of names. Hertzsprung and Russell. And I don't know if they worked together or separately, but I think they worked together. They came up with this diagram describing these different star types. So what they did, they plotted all the stars they do. Now this isn't in the sky, this is on a graph somewhere. The absolute magnitude, remember that's not the apparent magnitude, the absolute magnitude that depended on how hot the star was, okay, or how characteristic of the star, the absolute magnitude, and that's this scale here. Remember the biggest, the brightest up here, and the dimmest down here. That's how you do this. Plot the absolute magnitude versus the stellar temperature. Now here the temperature is lowest here, hottest here, sort of backwards for this, how they do it. The temperature that way. These are the really, really hot stars here, the coolest ones down here. Okay? And you plot that. Absolute magnitude versus the temperature. And I believe that is the surface temperature, if I'm not mistaken. Okay? And every star is represented by a dot here. Okay? Now, you wind up with most of what they call the main sequence stars in here. Sort of a purple eel here in the middle. The Hertzsprung diagram puts all the main sequence stars there. Our sun is right there in the middle temperature. Actually, it looks a little on the high side of temperature to me. And it's the apparent magnitude right around 5. Remember that. That's not it. Maybe that's what we were, 4.8 here. Maybe that's what that was coming from. I believe it was. Okay? So there we are, right in the middle where we always are, it seems like. Okay. But you have other groups of stars that are down here, here, and here. What makes those stars? Well, let's go to the red giants. Now, red means they're cooler. They're on this end of the scale, okay? But they're huge, okay? That's why they call them giants. Now, we'll see this in a little while, okay? So hang on to why they're that way. But the red giants, just keep in mind, those are stars that are usually pretty easy to see. Arcturus is a pretty big, bright star. Aldebaran is a pretty big, bright star. All of these are big stars, but they're cool stars. Then they have the novas. These are the supergiants, okay? And we'll get to why that's the case too. And these are some of the brightest ones you see out there. Antares is very, very bright, okay? Betelgeuse is pretty bright. Rigel, the Neb sort of, okay, they named several of them. But then you have some down here which are white dwarfs. Now they can be quite hot, but they're very, very small. And we'll see part of this too. By the way, here is Sirius. But they have a Sirius A and a Sirius B. Does anyone know why they say that? Sirius A and Sirius B? Actually, most of the stars you see in the sky are not single stars. Our sun is a single unitary star. Most of them out there are not. Most of them are binary or bigger clumps of stars than that. Sirius is a binary star. One of those is the main sequence star. Here, it's hotter than the sun. Its absolute magnitude is much greater than the sun. But it's paired with a white dwarf, which is quite hot, okay? In fact, hotter than this one, but quite absolute magnitude is very, very low. It's the star that's on its deathbed. This one's one that's still living pretty nicely. So basically, we're seeing Sirius A, okay? Well, Sirius B is a white dwarf. And we'll get to why it's a white dwarf later. Now, they throw in another thing here that they don't show there at all. And it really, I guess there was no better place to put it, but it should be on its own thing. You have something called a Cepheid, I don't even know how to pronounce this, variable star. Okay? What that is a star that pulses. It's sometimes brighter, sometimes dimmer, sometimes brighter, dimmer, brighter, dimmer. Okay? A variable star. And there is one little bitty paragraph in your book that talks about that. And that's at the bottom of the first column on page 361. Stars such as the sun emit steady light because the force of gravitational contraction is balanced by the outward flow of energy. The fusion energy moving outward, gravitational attraction pulling inward. It's balanced. Variable stars, on the other hand, are stars that change in brightness over a period of time. A Cepheid or something like that variable is slowly changing variable star that is useful to measure distances. There's a general relationship between the period and the brightness. The longer the time needed for one pulse, the greater the overall energy output of the star. The period brightness relationship to the distance was calibrated by comparing the apparent brightness to the absolute magnitude, which is what this does, true brightness of a Cepheid at a known distance with a known period. To me, that reads blah, blah, blah. I mean, they're not very precise in that, but that's what a Cepheid variable is. Why they put it on this, I don't know. They don't show an example of it anywhere here. But a guy named Hubble, there's another name, by the way. Where have you heard that name earlier in this class? The Hubble telescope. They named that after him. We'll find later, we'll refer to Hubble's law. Hubble was one of the preeminent, probably the most important astronomer that probably we've ever had. He covered a lot of ground. I think he was here in the U.S., and he set the bar for a lot of other astronomers. Okay? Come up with a lot of stuff like this. But Hertzsprung and Russell had done this before he came along. But that's it. Most of the stars out there probably are main sequence stars. They'll fall there. But you'll see them start drifting around the diagram as they age. And we'll see that a little bit later. I don't really care for the way the book put this together, but I try to follow the book because that's what you got to look at, the slideshow and everything else. By the way, looking back, I just about missed this. When we were doing this. What is the temperature of a star emitting light with a peak wavelength of 3,500 angstroms? Okay? There is actually a formula you can use, and it's given an equation on page 360 in between table 14.2 and the example. The relationship between peak wavelength and temperature is temperature is equal to 2.897 times 10 K angstroms, K being Kelvin, angstroms, divided by the peak wavelength, and that would be measured in angstroms. So that would give you the temperature. But frankly, what I would say, look at the diagram here. They said 3,500 is the peak. 3,500 would be, this is 2,000, 3,000, 4,000, 3,500 there. And the temperature would be probably somewhere greater than 10,000 K because its peak is here. So I would say, just looking at it, yes, about 12,000 K. What do they get here from the formula? Oh, wait, more than that. Nope. Don't quite agree with the thing here. It says 8,300 K, which is interesting. That shows it being the peak. So that's a little backward seeming. But again, they just sort of make up the problem here so they can give you a problem to do. A star emits light with a peak wavelength of 8,500 angstroms. Okay, that's even hotter than this one. What is this star's temperature? Its color and its type. The temperature, they say, would be 3,400 K, which again is not making sense according to this. A red star, and this shows it being a blue star, and type M, that's the same as Earth. No, it's actually cooler than Earth. We're K. So something about the table and the formula aren't jiving too well. And I don't know what the deal is with that. But anyway. All right. That's why I don't usually do much with the examples. They're not really very well defined. Okay. Now, seems like we've been here, done that, doesn't it? That we've already been talking about the life of a star. Well, we talked about the lifetime of a star, but now they're going to say, let's start with where we were to begin with. Where did we start? What was the star before it was a star? Yeah, a big, massive gases. That was called a nebula. Okay? That was long before. But it's nowhere close to being a star then. Once it has that perturbation, that shock wave, whatever it is that brings those molecules close together, and you start this gravitational collapse, that's when it becomes what they call a protostar. That's where a star begins. Yeah, before it was a mass of gases, but it starts with a protostar. Gravitational collapse. As that's collapsing, and this is what I was talking about before, the density is increasing big time. The temperature is increasing big time. The pressures are increasing big time. Okay? All these are increasing. Density, because that's mass per unit volume, is density. Temperature, as you get more mass in a smaller volume, the temperature goes up, and the pressure is force per unit area. That's certainly going up. So all these are increasing. Now, somewhere around 10 million K, that is really hot, folks. 10 million K, fusion begins. They call it the fusion ignition temperature. That's where fusion of hydrogen into helium starts. And once that begins, basically you have an explosion of energy. Up till now, everything's been shrinking. At this thing, it starts blowing up, okay, and pushing out. Now, what you have to achieve ultimately is some type of dynamical equilibrium. That's an interesting combination of words. Equilibrium means equal situation, okay? Dynamical means it's changing, okay? So this equal situation is coming by various things. You've got the inner force of gravity, the outward pressure of the fusion energy, and it has to sort of achieve some type of a balance, okay? Once it does, it enters the main sequence. So going back to Hertzsprung Russell diagram, Russell diagram, I can't talk, that's when it becomes a main sequence starts. Before that, it's a protostar. Now, in that time period, there's lots of changing going on. The explosion happens, it tends to blow up, the gravity pulls it back in, and there's probably a lot of radiation, probably a lot of mess going on. I say that because we're going to see some of that mess in a later chapter, not even in this chapter, okay? But hang on to the concept, okay? So, when it reaches in the centermost part of that protostar, finally reaches 10 million K, the temperatures keep going up, the density keeps going up, the pressure keeps increasing. Everything is, when finally it reaches that 10 million K, then fusion begins and it starts blowing out. So the inward force of gravity, the outward force of the fusion in the core, moving things outward. And when they finally reach some sort of equilibrium there, dynamic, it may still be pulsing a little bit or whatever, that's when the star enters the main sequence, when it sort of settles out there. Okay? Now, that's how it begins. And it may live in that main sequence. Remember, small stars will live in there trillions of years. Big stars, only millions of years. Average stars, billions of years. So they may be in here for various lengths of time. Okay? These may be there for a long, long time, and these may be there for a shorter time. These billions. Yeah, still, all those are long time. Millions of years is a long time to me. Okay? So they enter. Whoops, I went too far, didn't I? No. Okay. So that's when you go into the main sequence, and you live there a long time. Okay? But after a while, remember you got hydrogen fusing to helium. After a while, all the hydrogen gets used up. For our sun, that's taking a total of about 10 billion years. Bigger stars, much less time. Smaller stars, greater time. But at some point, and it all starts because you have the hydrogen fusing to helium, you don't have any hydrogen anymore. Okay? The hydrogen in the core is exhausted. But what happens now? When there's no more hydrogen to fuse into helium, it collapses. Because remember, the fusion is what's pushing outward. Now it collapses. Boy, when it collapses, though, it heats up big time. I mean, much hotter than it was before because of gravitational and friction and things like that. Okay? Well, if it gets hot enough there, okay, the core is collapsing and heating up big time. The outer shell is expanding, and that's because of the heat from in here is pushing the outer shell outward, and it cools. Okay? That's what gets down to a red giant. Because the outer shell is bigger, that makes it a giant, but it's cooler, and that's what makes it red. Okay? Core is collapsed now. Now, hang on to that. We don't know where to go. Let's give the lifetimes again. The O stars, which are the hottest stars, millions of years in the main sequence. The M stars, which are the very coolest ones, those are the trillions of years. We're right in the middle with the, what were we? K? Did I say we were? Huh? Yeah, G star, yeah. We were G. Okay. We're in the billions of years. And there's lots of ranges in there too. So, we've got down to this, the red giant. We've moved out of the main sequence because we've burned up all of our, or fused all of our hydrogen. The core is collapsing, the outer shell is expanding and cooling and going red, but going bigger, so it's a giant. The mass also determines what the ultimate fate of the star is. The mass determines how long it's going to live. I've got a sneeze again, I'm so sorry. But it also determines what will it become. So now the next slide is going to focus on that. Well, let's start with this. Main sequence. Remember Hertzsprung, Russell diagram, the absolute magnitude and the star temperatures. Now this scale may be somewhat compressed from what the other one was, because notice this is going from plus 16 to minus 8, M to O. Now let's go back and see what this one was. It was minus 10 to, yeah, it's about the same, M to O, but it's flattened out some. So this is longer this way and shorter this way. So it's condensed this way and expanded that way. So our snake would be, or our eel would be like this. Okay? So this may start in the main sequence, but then when it's used up all its hydrogen and the core collapses, the outer shell expands and cools, it moves up and becomes a red giant. Okay? Now, it does some other changes here and ultimately gets down here. This is the white dwarf. It may or may not go through all these changes to get to this. That depends on how big the mass was to begin with. So let's see where these go. Okay. This looks a lot like the last one we saw. The late red giant stage. It was main sequence, went to red giant, and then moved up to a bigger red giant because the outer shell is still expanding and cooling, so it's moved on up. Now, but the core has collapsed and is heating up. Well, as that heats up, now what's in the core? It was hydrogen. Now all the hydrogen is fused to helium. So you got lots of helium in there collapsing on itself, heating up. Well, as that core collapses and heats, now you might get hot enough for helium to fuse to carbon. And if that happens, and it typically will in most stars, now you get fusion again. So the radius and the luminosity decrease. It doesn't make a lot of sense why the radius decreases, except now you've got a lot of mass pulling it back in, but the luminosity decreases. It moves back toward the main sequence. So this may be back in the main sequence again. I don't know. It could be. Hard to say. Could become the main sequence stars again because it's got fusion going on. So it's acting more like a star. So that has happened to all these stars. The very small stars, the medium stars, the large stars. Okay? Now, for the less massive stars, what happens? You use up the helium really, really quickly because you weren't that big to begin with. And whereas you had so much hydrogen, it takes either 2 to 4 hydrogens to make one helium, so you have a lot less helium than you had hydrogen to begin with. But when helium fuses to carbon, it takes even more helium to make carbon, so it's going to happen much faster. So now you don't have any helium, you don't have any hydrogen, those fusions have ended, so what has happened? The shells, the helium and hydrogen there are used up, the instabilities blow off outer layers of the planetary nebula, okay? So in other words, once the helium is finished, it collapses again, it heats up and basically blows up. And the outer shells go way out here, and your inner shells sort of collapse on themselves. Okay? This is called the planetary nebula. This isn't quite like the nebula before. What you have now, let's see, they may have a picture of it. Let me see if they do. Yeah, there's one. Your core is down here. It's collapsed on itself, and that's probably carbon, because helium fused to carbon. Very hot conditions fusing to carbon, okay? The outer gases that were your radiation zone and your convection zone, they've blown out. And this forms another cloud of gases, and that's called your nebula. Cloud is a nebula, and it's called a planetary nebula because it goes around the core, like the planets go around the sun. So that's what it's called. It has nothing to do with planets. It's just called the planetary nebula. Okay, that carbon core in the middle, it contracts to become white. White because it's very, very, very hot. Not hot enough to be blue, but white. But a dwarf because it's tiny. It is incredibly tiny compared to what it was. Okay? Now, that's called a white dwarf. As it cools, it loses the whiteness and just becomes a black lump of carbon. Now, the black means no light is coming out of it. It doesn't mean the carbon looks black. We think of carbon as being black. Several years ago, I'm guessing around 10 maybe 15 years ago, I had a guy that worked with me here. He was an adjunct, part-time. His name was Dr. Bolshinsky. He was Russian by heritage, but I don't know if you know the history of the Soviet Union. Russia was the biggest country in the Soviet Union, but it had these other countries that it surrounded itself with. There was Ukraine, Belarus, Tajikistan, Kyrgyzstan, all these others. They were all in there, and that was the Soviet Union. Well, Russia didn't like the other countries. They didn't want them revolting. So they sent Russians out to live in the other countries so to dilute the population and to keep Russia the strongest. So even though his family was Russian, his family was sent to Ukraine. Okay? But the Soviet Union was one big country, you might say. And the Soviet Union had a space program, they had the military, they had everything else. And he worked with the Soviet Space Agency. Okay? They beat us to outer space, they beat us in several ways, but we beat them to the moon. They beat us in manned space flight, several things like that. And Dr. Bolshinsky had worked with the Soviet Space Agency. But then the Soviet Union fell apart. And he was living in Ukraine. We wanted to move back to Russia because his family was Russian, but they wouldn't let him move back because if you were living in Ukraine, you stayed in Ukraine. Actually, Russia wanted it that way because they wanted a good Russian population there to keep them favorable to Russia. Okay? And you know, a lot of things today, the activities going on between Ukraine and Russia, but not very happy activities. There's been changes of government from a pro-Russian government to an anti-Russian government, so there's been a lot of problems there. That goes back to that same issue. Well, so he couldn't work with the Russian space agency because he lived in Ukraine. Ukraine was too poor to have a space agency, so he moved to the U.S. But he couldn't work for us immediately, so he was just doing whatever he could. U.S. the land of opportunity, so he was working here as an adjunct instructor, which doesn't pay all that great, but we got him as many hours as we could. He was a really good guy. And he talked about the first white dwarf that they discovered. And you know what they named it? You will name these things. They named it Lucy. Can anyone think why they may have named that white dwarf Lucy? Say again? Okay, it's actually related to a song.
So a song?
A song. A Beatles song, no less. What do you get when you take carbon under enormous temperatures and enormous pressures? What does it become? Do you know? Diamond. Diamond is pure carbon, but it's just going to go an enormous amount of pressure, enormous amount of heat. We'll see that later in a later chapter too. So the white dwarf, which was a carbon core that has been compressed under enormous pressure and enormous temperature, the odds are a good part of that is diamond. So the name Lucy, Lucy in the sky with diamond. I can't sing. You never heard that Beatles song? You poor people. Okay, go back and check out, yes.
I have a couple of questions. Okay, you said that the class lecture would be mostly the first half, and then the second half would be the labs. If we're unable to stay for labs one day, what would we do to be able to complete the lab?
Okay, if you can't be here when we actually have a lab, I'll record, just like I record the classes, I record as much of the lab as I can get on there. Now certainly, and not many of our labs are going to be hands-on, a lot of them are going to be paper labs, so I'll try to record as much of that as I can. But when we are making measurements and stuff, and a few of the labs do that, or there'll be computer labs and then you can hear what the instructions are, you can do it at home. But again, watch the YouTube videos and you can get a lot of it. Anything you can't get with a friend, pair up with somebody and say, are you going to be here? Can you take notes for me and get the rest of the lab that you might not be able to get off the question.
Okay, today I'm not going to be able to stay for the lab because I'm kind of starting this class and didn't know there was a lab with it. So what do I need to do to make sure that I prepare for myself?
Okay. What I would say is continue reading in the chapter because we're not going to finish the chapter today. We're going to continue in the lab period. It's going to be just like this. So when you get home now, let me talk about the problem with the YouTube. Okay. Like I say, the first class I did this morning is already uploaded to YouTube, but I haven't moved it into the playlist yet because I didn't have time. The second class is probably already uploaded. This class we're still recording. So this class will probably not upload until sometime late this evening. Now, if I happen to be on the computer when it does upload, then I'll do it. But then tomorrow morning I start with another class and another class. So it'll probably be tomorrow afternoon before I get it moved to the playlist. It may be sooner, but my guess will be sometime after 2 tomorrow before it actually gets on the playlist. Because Mondays and Wednesdays I have office hours. Tuesdays and Thursdays I have almost none. I have a few at the end of the class period today, but I'm doubting whether this class will be finished by then. The first 2 I'll upload then. But the other, if I have time tonight, I will, but otherwise it'll probably be tomorrow afternoon. So watch the video, and I doubt if we'll get to the lab today, but we probably will come pretty close to finishing the chapter. Okay, here's another thing. The test, I never give you the test on the same day we finish the chapter. It's always going to be the next class day. So let's say we finish the chapter 14 today. That means Thursday we'll have the last 30 minutes of the test, the 2 hours before that of lab, and then what will we have? Only about an hour or something to go. We'll only have a very short class on Thursday, a lab, and then a test. So that's how we'll usually do.
I just want to make sure that I be prepared for the next class.
So listen to it and find out how far we got. If we don't finish chapter 14 today, we'll finish it in the first part of Thursday. Then we'll have the lab, but we'll wait till the next Tuesday to have the test. All right. So that was probably way too long talking about white dwarfs here. Okay. This is the time between class and lab, technically. Do y'all need to take a break? I could probably use one myself. So why don't we take a real short break? Let's try to keep it 5 to 10 minutes.
10 minutes.
Okay, closer to 5. But I'm going to pause this for now. And be sure to remind... Okay, and again, I'm a little sorry that it was more than 5 to 10 because I got a phone call right at the end. But I was trying to get back. Okay. There is another little blurb, and I sort of meant to say this earlier. Concepts applied. Sometimes these are pretty good. Sometimes they're maybe not worth too much, but this one seems to be okay. Seeing the spectra, when we were talking about the visible spectra, they say inexpensive diffraction grading on plastic film is available from many scientific materials. So, was it? Oh,
We didn't know if it was recorded. That's all.
yeah, it is. Okay, got it. Thanks. Glad you're watching for that. Well, now that I read this, it may not be as good as I thought it was. For many scientific material supply houses, if available, view the light, blah, blah, blah. If you want to do that, it's worth it, but I thought they were going to give you a cheaper way than that, but whatever. Okay, so where we got last time was the less massive stars. They do go through the gravitational collapse. It heats up enough. Die, right?
Yes, sir.
Middle part of the alphabet hung in there pretty well. It's the, well, we got pretty good numbers back. Okay. 3 at the beginning and 1 at the end. Haven't made it back yet. Okay. So the less massive stars, everything goes through. And here we go. Here's Chris. Right? Okay.
I'm watching my roommate's dog, and then put him up. So I had to go.
That's all right.
I'm sorry.
All right. So even the less massive stars, all the hydrogen's used up. It collapses. The core collapses on itself as the outer ring is blowing up. That makes the red giants are increasing and cooling. But then when the core collapses enough and heats up enough, then it takes a really hot temperature now for helium to fuse to carbon, so it starts blowing up again, and I still haven't quite figured out why the radius decreases then. It seems like it would be going out, but it does decrease. Luminosity decreases, moves back toward the main sequence then. But then all the helium is used up. At this time, the instability, the core collapses again, and that's when a huge amount of heat, that's what makes it white now, even though it wasn't that hot a star to begin with, it collapses on itself, and the gases on the outside blow up. Okay? And that's what gives you the planetary nebula. These are the gases around here, and the carbon core in the middle. Very hot to begin with, making a white dwarf, but then later it will cool just to be a colorless, with no light coming out of it. It produces light to begin with because it's so incredibly hot. Okay. Now, let's go to the more massive stars. And by the way, let's go back because this is, main sequence, beginning, move into a red giant, moves onto that, back to main sequence maybe for a little time, because when the helium is fusing carbon, blows up again, moves up here to what they call the massive giants or something. Actually, this may be main sequence over here. I can't quite figure it, but here's the white dwarf down here. Okay, so that's where you end up here. So I guess that's the main sequence up there, and those are just moving around in the red giants. Okay. So let's go to the more massive stars. Okay, more mass, more gravitational contraction, more heating. Now the critical temperature, remember it was 10 million degrees K, 10 million K, that you don't use degrees with that. Now you start fusing carbon fusion. And at this time you form even heavier nuclei, up to iron. Carbon fuses to some and then others to others, and it goes up to iron, it won't go any past iron. But at this point, all the fusion energy sources are used up. So now you've had even higher degrees when you've got gravitational collapse, contraction, and heating, when you've got more and more mass there, and you have carbon fusing to the heavier nuclei, and now the energy for expansion pressure is lost, so the dynamic equilibrium is disrupted, and now the whole thing, now this is really, really massive. It collapses on itself. I mean, it's a huge collapse now. And this is leading to the supernova. The star collapses on itself with such force and such vigor and so much energy that it rebounds from the core. I mean, it's sort of like throwing really hard a basketball against the wall and it bouncing off really hard. Rebounding from the core, and the elements beyond iron are created in the explosion that happens. Because iron will not happen just in the natural sequence, but when you have all this extra pressure and the rebound here, that's where your elements beyond iron come into play in that explosion, and then they're distributed throughout the universe because the supernova just blows it everywhere. Okay? The subsequent events depend on how big the mass is in the remaining core. Now this was the whole mass of the whole star. If it was big enough, you get carbon fusion that leads to heavier elements up to iron, and you get the supernova, and that huge collapse and rebound, that gets elements greater than iron, beyond iron in the periodic table. And then what happens next depends on how much mass is in that remaining core that's left there. Things have blown up like crazy, but you still have a lot of mass there. So we have two more divisions. Now, they show on the slide that sort of makes sense. And the thing in the book, and I think will come up in the slide later, it doesn't make as much sense. But this, now you've blown lots of stuff out, the remaining core, the core, okay, is still between 1.4 and 3 solar masses. If it's that big, okay, that means 1.5 times up to 3 times our whole sun. This is only in the core that's left. The gravitational pressure fuses protons and electrons into neutrons. Remember, the protons are positive charge, electrons negative charges. You have a very major nuclear reaction going on here, fusing the protons, electrons into neutrons, and you have no more charge, okay? Now, this forms what they call a pulsar. You can think of this as a pulsing star. That's kind of where what the name means. And this neutron star, by the way, is incredibly dense because, remember, the electrons take up most of the volume of the atom. The protons and neutrons have most of the mass, and they're in the center in that nucleus. But most of the volume is occupied by the electrons, which are almost no mass. So most of an atom is empty space, all the space in there. All the masses down here and electrons out here with almost no mass and empty space in between. Well, now when the electrons have been fused with the protons, and all you got is neutrons, there's no empty space left. I mean, it's just really, really, really massive there. Okay? And that's why they call it a neutron star. Now, it's rotating, and as it's rotating, and I cannot answer the question why it's magnetized, but many of them are. Okay? There must be some residual charge somewhere, because that's what makes a magnet, a moving charge. I just don't know where it comes from. So anyway, it's magnetized, rotating, neutron star, and this produces a pulse. Because the star doesn't just spin on its axis like this, it also precesses. Have you ever played with a top? Or seen anyone play? Or seen a video of someone playing with a top? When you spin the top, it stands almost perfectly straight, but then as it slows down, it starts doing this kind of motion, and then finally it collapses. Well, that's called precession. And that's what happens as it precesses. You get the intense field at the poles, and then it's neutralized, and then the intense field at the other pole, and that's what gives you the pulsar. Now, later in the chapter, a woman will be introduced who discovered the first pulsar. She was working in a laboratory then. She was a grad student, I believe. And she discovered the first pulsar. And there were all sorts of ideas of why it was, but she did so much of the work in it. Her name, and we'll get to it later. And the sad, sad thing, and some of this might be because she was a woman, but they gave the excuse of something else. Because she didn't have her PhD yet, she was still a grad student. The person who got the Nobel Prize in Physics for it was her boss, not her. He had the PhD, she didn't. And it probably was a little sexism going on there, more than likely, okay? But their excuse was she wasn't in charge. She was an underling. Yeah, bigger, yeah. Okay, so that's what happens to your your very massive stars between 1 and 3 solar masses. But some of these stars, the core that's left over, remaining core, is greater than 3 solar masses. And somewhere around in there, around 3 solar masses, now the gravitational collapse overwhelms not just electrostatic forces, positive and negative, all known forces whatsoever. And what you have left, we don't even know. It's just such a tight collection of whatever it is that not even light escapes. In fact, all energy tends to be pulled back into it. That's called the black hole. You probably heard about these. And I'll tell you now, the current thought is every galaxy is surrounding at least one really major black hole. And sometimes when you have star clusters within a galaxy, they're around black holes as well. So there's a lot of them out there, but the thing is the gravitational collapse overwhelms all known forces, not just electrostatic, all forces. Even light cannot escape. They may be hot, they may be incredibly hot, but light can't come out because everything is sucked back in to the dense, compact object, whatever that is at the center. Yes?
How do you figure out the black hole when you like H go inside the hole, can't come out?
So this
How
one,
do you figure out the black hole when you go in, can't come out?
that's what the theory is. But then the idea is, why are they not becoming more and more massive all the time? And it doesn't seem like that's the case. And no one can quite figure out why. I think, who is it gave me your paper topic, and I was going to do Stephen Hawkins. That was you, okay. I believe he came up with a theory that seems to jive with what happens to some of that. That some things do escape. We just don't censor what they do. I don't know if you'll get into that in your thing. Stephen Hawkins, by the way, recently died. I mean, just in the last few months. He was an incredible mind, an incredible person too. And unfortunately, what he'll probably go down among scientists, they'll celebrate and recognize all his accomplishments. But what everybody else remembers him in, he had ALS. You know what that is? It's some sort of sclerosis. That's the S part. I can't think what the AL is, but it's often called Lou Gehrig's disease. And you know what? Is anyone familiar with that at all? Basically, your body quits on you. Your nervous system, from what I've read, it usually starts with a tingle thing. You drop things easily. You can't figure out why you don't have as good a muscle control as you did. And then it progresses. And basically, the nervous system stops sending signals properly, or they don't get received properly or something, and you lose all things. Your mind is still as sharp as it ever was, but your body is giving out on you. I mean, you can't do a thing. It starts out with just clumsiness. After a while, you're in a wheelchair. After a while, you can't talk. You know, it progresses in different speeds in different people, but ultimately, usually what gets you is stop sending the signal to the lungs and you stop breathing. You know what's going on. It's not like senility or anything else. You know exactly what's going on, but you can't do a thing about it. Well, Stephen Hawkins was such an incredible mind, and his disease was rather strange too. He's got it way younger than most people do. I think he was still a grad student when he got it in his 20s. But it didn't progress as rapidly in him as it did others. But even when it did start progressing, I think the nation of England, he was in the British Commonwealth, he was English, and I think they provided the health care that he needed. And at the end, he couldn't move, he couldn't do anything. Someone had to take care of him. He had just a whole bevy of nurses that ran shifts around taking care of him. He couldn't eat, he couldn't swallow, he couldn't speak. But he gave lectures because of him, they developed computerized speech things, and they got it to be as close to what his voice was before he got it as after. He's incredible. He showed up on The Big Bang Theory at least once, as a guest star. Of course, he's in a wheelchair, he can't move, he looks like a, complete invalid, which he was, but he had this incredible mind, and he wrote books, and of course it took him forever to write a book or to record a lecture, because he had, everything was slowed down, and finally his body did ultimately give out just recently, but he lived for decades in basically a vegetable-like state, but his mind was still good, and he didn't know. I had never heard of Lou Gehrig's disease except through Lou Gehrig until Catfish Hunter got it. He was a pitcher for Mets or somebody, and it seemed like baseball players. But then I found out football coaches, but it seemed like sports. But then I read about women getting it and stuff, but men are more likely, it seems like, to get it. But it didn't seem to be any rhyme or reason to it. But when I moved to Birmingham, I just heard these other things. I was working at Southern Research Institute, and I was working with a very top technician we had there. He could do anything electrically, mechanically, and stuff. He was just a great guy to have, and he needed a project. I was working on a project, so I worked with him some. And this one he said, I can't grasp anything in my either left or right hand. I don't remember now. And I said, well, my dad was like that. He had arthritis. You might want to have that. No, they checked for that. They don't think it's arthritis. And so anyway, he was seeing a specialist, and he came back one day and said, I have ALS. First person I've ever known in person to have it. Well, within a few weeks or months, a neighbor of ours said their pastor had ALS. I said, wait a minute. I've never known a soul with ALS, and just within a few weeks, I know of two. I didn't know the pastor. I knew this other. And when I mentioned this to my technician, He said, yeah, we were in the doctor's office the same day. We got the news the same day. Well, the pastor died in just a few weeks, and as far as I know, the other guy lived for many weeks or months longer. I'm sure he must be dead by now. I no longer work at Southern Research. But then when I came here to work, and this was just within a year or so, came here to work, the librarian who was here at the time, within a year or so of my being here, her husband was diagnosed with ALS. I said, what is going on here, you know? And over a series of a few years, he was dead too. And I'd seen a football coach somewhere in the area that had it, and they were documenting his digression, but it must be more prevalent than I thought it was. I thought it was very, very rare. But one of the scariest diseases in my life. So I think I've forgotten, Stephen Hawking has a theory about why it doesn't keep getting more massive. I think they do get so really massive, but nothing goes out that they can detect. Now, there's lots of other theories. There are some theories about multiverses, in other words, parallel universes, and where we may be a matter universe that's somewhere adjacent or at the same time there's another whole universe called an antimatter universe that may be parallel to us, and it may be the masses going into our black holes and coming out something on their side, and then the reverse of that. That's way beyond my ability to conceive. What's that? Yes, they do. Science fiction and science, you can't tell where one ends and the other begins on that. Yeah. Okay, so that's what happens to the very most massive stars. They ultimately become black holes. The really big stars, but more massive, they become neutron stars, and then the rest of them white dwarfs. Okay, here is the diagram. Now, the one in your book is a little bit nicer than this one. The slide set are from an earlier edition, and I didn't get the slide set for the new edition, but it's basically the same thing. What started as a mass of gases, huge massive gases out there somewhere, you get some sort of perturbation, something that a shock wave that comes in and forces some of these closer to each other, and then they start sticking to each other, gravitational collapse, and then this goes down to a protostar. The protostar is the gravitational collapse, collapsing, getting hotter and hotter and hotter, and when finally you reach the point where it's no turning back, now this may collapse and then re-expand, collapse and re-expand. But when it becomes a protostar, there's no turning back. At that point, it's going to be a star one day. Okay? This may not have been, but this has reached that point. Well, when it finally settles out, you get the dynamical equilibrium there, then it becomes a main sequence star. Okay? Now let's go to the low mass star. When it burns up all of its hydrogen, okay, I say burning up, fuses all of its hydrogen to helium, no hydrogen left, the core collapses, and the outer parts expand, get cool, and they become red giants, okay, outside the main sequence, okay, above and to the right. They're much bigger. It was here, much bigger, but not as hot. Easier to see because it's so big, but it's a red giant. Then it could collapse again and fuse to be helium to carbon. Then it may temporarily go back to the main sequence, but then when it's all over, it becomes a white dwarf. Starting with the planetary nebula, it disperses after a while. It's a cold, that's a better term for it. They say lump of carbon. Now, the odds are there's a diamond in that carbon. Okay, because all that heat and pressure more than likely was. Okay, but the rest of it may just be carbon. Okay. Now, the mid-mass stars are, this is the low-mass stars. They don't go back to the main sequence, okay? They just collapse from the red giant to be a white dwarf with carbon. The main sequence stars that are mid-mass, they become bigger red giants when they use all their hydrogen to helium, then they expand and become a planetary nebula, and if they collapse again, then that goes to the white dwarf, and that becomes full-blown carbon. Now here's the part that, to me, they got backwards. I mean, it's okay, but the main secret stars, the big, huge, massive main secret stars, really become real big red giants as they are expanding there the first time, and then when they collapse maybe multiple times, and the last time the carbon has been fusing to iron, the larger molecules including up to and including iron, when that explodes, that's a supernova. This is a planetary nebula, just the outer ring of gases blow off, but this is a major, major explosion, and that's what forms the heavier metals beyond iron, or elements beyond iron. Now, this is the part that doesn't make sense. The neutron stars, they should be down here, and the black holes up here, because the next massive big, when the core mass that's after the supernova has occurred, the core mass is still 1.5 to 3 times what the Earth was, total Earth is, then that becomes a neutron star. The last collapse fuses the electrons with the protons, and you have only neutrons, maybe with a few other charges. Those neutron stars are very, very, very dense, and probably very hot, because that dense you would have to be, and possibly looking like a white dwarf or bigger, but that's what's left, and they pulse as they spin and precess. But then the huge masses, more than 3 solar masses left in the core, when they finally collapse, they don't just fuse protons and electrons, they fuse everything, and it becomes a black hole. And that's sucking in everything. No light escapes. The reason this is black is not hot enough. The reason that's black, light can't escape, no matter how hot it is. Okay. Now, yours in your book has a little bit fancier graphics, but it still has a black hole inside the neutron star. I would rather reverse those because the masses are different there. Okay, any question on stellar evolution? Okay. There is a incredible picture, I think taken by Hubble Heritage Team. The blown off outer layers of stars can be beautiful ring-like structures as seen here in the Cat Eye Nebula. I believe this is one of those 10 that you see in your, that I put out there on Blackboard under, what did I say the name of that was? Class handouts and other stuff, or something, whatever it called that. And that's a pretty neat picture there. Okay, that takes us stars, the beginning, their ends, and all that kind of stuff. Now, there's a few figures in your book that are not besides that one. The figure of the neutron star, that's figure 1414. The magnetic axis of a pulsar is inclined with respect to the rotation axis, and therefore the rapidly moving electrons in the regions near the magnetic poles emit radiation pointing outward, and when that beam sweeps past the Earth, a pulse is detected. Again, sort of blah, blah, blah on the description there, but that's what creates the pulsing. Now, observing with new technology, this is pretty interesting. Don't think you're responsible for all this stuff, but new technology gives us new ways to look at different things, and this shows you several of them. The Chandra is X-ray telescopes, as is the XMM Newton. The Spitzer Space Telescope uses infrared telescope technology. The Fermi Gamma Ray Telescope is Gamma Ray Telescope, as you might guess. Arecibo Observatory radio telescope, and then Very Large Array, VLA, is there's two different ones. One, Arecibo, Puerto Rico, that's where it gets its name, and the other is New Mexico, and these are radio telescopes as well. Okay, so you start looking at different things, you can get different information. All right, now we're one more. Light pollution. It's really not pollution, but it sort of acts like it. The third lab that we do in here is going to involve observing the moon and stars around it and that kind of stuff. One of the problems you'll have with it is a problem that's really common is what we call light pollution. If you live anywhere near Birmingham, you're going to have a hard time seeing as many stars as people who live further from major cities. Bessemer, you'll see a few more maybe than you would in Birmingham, but still not as many as you see out in the country. I'll tell you sort of a dumb story here. It's true though. When I was an undergraduate, I went to Georgia Tech, and my sophomore year I started working in the dorm system. I was what they call a student counselor in the dorm system. Then my junior year I became a senior counselor in the dorm system, and some guys moved into the dorm. I got to know some of them, but included in that was my younger brother. They moved in my junior year. I was still a senior counselor in that same dorm my first quarter of my senior year. Later I moved to a different dorm, but I got to, my younger brother was a freshman my senior year. And he got to know these same two guys, many others, but two that were living up on the hall in my dorm. One was from Boston, Max, and one was from New York City. I think his name was Bob. And Dan got to know them pretty well, and I was working on campus and had a lot of stuff going on. So very seldom did I get to go home for a weekend. Dan, on the other hand, he was living easy and not doing as well in school, but doing okay. But he went home fairly frequently. Now, of course, he used my car because he wasn't allowed to have a car on campus. I was, but I was working on campus anyway, so he would drive home. So he invited Bob and Max to go home with him one weekend because he got to know him pretty well. We lived way out in the country. The nearest flashing yellow light was 7 miles from our home, okay? The closest stoplight was 10 miles from our home. And the closest city of any size was Augusta, Georgia, and that was 25 miles from home. So we were way out in the country. And when Bob and Mac and my grandmother was sick by then, so she was staying in my parents' house. So when guys came, either my brother or me or my older brother, they usually stayed in my grandmother's house just to have somebody in the house. Lauren is back. Oh, you were here before, weren't you? No, you weren't. Okay. You just have time. Okay, now all we're missing is Jessica and Christy. Christy hasn't come. Oh, yeah. I'm sorry. I missed you when you came in. Okay, good deal. So all we're missing is Jessica. Okay. And then Corey wasn't here to begin with. Okay. So anyway, they were staying at my grandmother's house. Now, I'm not going to say that they didn't have a little bit of stimulus in some nature, either liquid, gaseous, or otherwise. But they had been inside in the evening, and it was a clear, I think probably spring evening, clear skies, and they happened to go outside. And like I said, Bob and Max lived in New York City and in Boston. And they had never been out in the country before, not like this. They went out and saw the stars they had never seen a display of stars like that in their life because they had lived in cities. And you only pick out a few stars, you could almost count them, you know. And here, the Milky Way, I mean, everything was. And Dan said they just went tearing across the soybean field. Look at that, you know, yelling and screaming. Of course, they're out in the country. It wasn't going to bother anybody. Dan said it was the funniest thing, but they had never seen that. That's what light pollution's about. You just don't see them because you have other sources of light. Just like, not as much as the sun, but the sun has reached out to every star out there. Those stars are still there. They're right out there, but the sun just bleeds them out. It's the ultimate polluter of light. Okay? So you can read this if you'd like. It's a pretty good little blurb at the top. Okay. And then figure 1415 is a pretty interesting one, too. It's a jet of particles stream from the center of some galaxy going at nearly the speed of light, and the jet is powered by the monstrous black hole. Now, this is interesting because they say this, if you read what it says, a jet of particles stream out of the center of a galaxy M87 at nearly the speed of light. The jet is powered by the monstrous black hole. So here's something coming out of a black hole that's not supposed to emit anything. So it's sort of what you were talking about before, and I think probably fits in with what Stephen Hawking said as well. Okay, so let's move on to larger scale structures. We've been talking about stars. Let's go to bigger things. Binary systems. I already mentioned this when we talked about Sirius. Two gravitationally bound stars. Most stars that you see out there in the sky are binary pairs. Most of them are. Ours is just one of the few that is not. There's one place that our sun is pretty special. It's a unitary star, not a binary star. Most of them are in pairs. Now, going back to the idea of can you have life outside of Earth? Okay, now I know that isn't anything the book's talking about now, but it is something that comes out of this. Frankly, I wonder if there are planets going around a binary star, which is two stars gravitationally bound to each other. Either you're going to be too close to one or too far. I mean, I don't know how you could have even enough temperatures and other things to support life. It seems like the extremes would be too bad. You get on the side of the hot star, too hot. On the side of the dead star, dying star, too cold. It just seems like it would be a lot of a problem there. So I would think most binary stars are going to be tough to support a planet that could sustain life. Now maybe there's enough unitary stars out there that could, but you still got all the other really intricate details to meet. Okay. Next you have star clusters. These could be tens to hundreds of thousands or more gravitationally bound stars. Now these aren't going to be super close together, but just bound relatively close. Often will share a common origin, like one big nebula and several stars came out of that, or a smaller black hole that's pulling them in. I think it could be either one of those. But then after that, you get to your galaxies. Now, believe it or not, the galaxy is the basic unit of the universe. I would have thought, before I started teaching this course, if you'd have asked me the question, I would have said star is the basic unit of the universe. No, galaxy is. How big is a galaxy? Billions and billions of gravitationally bound stars. Not just up to hundreds of thousands, but billions of billions gravitationally bound stars. Now, not just that, just like you have star clusters, you can also have clusters of galaxies. And superclusters of galaxies. And overall, we have billions and billions of galaxies. I don't know if y'all remember the old TV show, Third Rock from the Sun. Probably not. But it's almost the third speck of dust from this little insignificant star in these huge galaxies and then there's billions and billions of galaxies. Yeah, there's got to be, just the law of averages, you got to have some other planet that probably could sustain life too. But the chance of ever finding it is pretty slim, I think. Okay. But it's a big, big world. And we are such an insignificant little part of it. We think our country's big. Our planet's big. No, we're pretty small. Okay? Well, our galaxy happens to be the Milky Way. I mentioned that earlier. That's that sort of diffuse line of stars. I've never seen the Milky Way since we've lived in Birmingham. I go home to the farm, I can see portions of the Milky Way. But you can't see it. Light pollution. It's visible as a diffuse band on a really dark night. If the moon's out, you probably won't see it. A dark night. Billions of stars, some bound in galactic, I think that should be star clusters. Okay? And the structure is a galactic nucleus, which has billions of stars in it, and then a rotating galactic disk of a diameter 100,000 light years. Remember how big a light year is? This is in 100,000 of those. That's the diameter of our galaxy, the Milky Way. Now, there's not just that. That's this disk that's around it like this. Then there's a galactic halo that's completely around it, and it contains about 150 of these globular clusters that are outside the disk. Let's see if we can get a picture of it. Well, first there's what you see in the night sky, and this is magnified and accentuated in a very clear sky on a very dark sky. I'd say completely moonless, a new moon. You don't even see it. And that's as bright as I've ever seen the Milky Way. Most of the time it's a lot less bright than that. You can't pick out the individual stars. They're just too many, too close together. It's just incredible. And you're looking into that galactic disk. Okay? Here is the what they're describing here. The galactic nucleus, again, you awake yet? Okay. Which is just a, sorry? Okay. A huge mass of stars. I say relatively close together, tens, hundreds, thousands of light years away apart, but still, on this scale, it's pretty small. That's your nucleus there. We don't live there. We're not there at all, okay? And then you have these spirals of stars, at least two they show here, it may be actually more than that go around like this. That forms your galactic disk. This is looking from overhead. This is looking from sideways, okay? Now this is your galactic halo that you have there. We live in the one of these spirals about 2/3 of the way out from the nucleus. And basically, when you see the Milky Way, you're either looking this way or that way into the spiral. I don't think there's any way you'll see even anything. Maybe a little bit of the galactic disk. You're basically seeing most of the stars right here. That's mostly what you see. Now, looking up and away from the Milky Way, you see some of these that are in the globular clusters, okay? The halo of the globular clusters. They are outside of that. And then you can actually see some things like the next closest galaxy, Andromeda, you'll see somewhere out here too. It's pretty dim, but you can see it. And the Hubble Space Telescope is taking some neat pictures of it. So what we see is just a tiny, tiny, tiny fraction of what there is just in our galaxy, and we can't see much beyond that at all. Okay, so let's talk about those other galaxies. Our very nearest neighbor, now we're talking from the Milky Way, not the sun or us at all. The nearest neighbor to the Milky Way is called a local group. Okay? This local group is made up of a few dwarf, really small galaxies, galactic clusters type thing. These are no more than 1,000 light years in diameter. We're 100,000 light years in diameter. These are like 1,000 light years in diameter. Still huge, but not enormous. The nearest dwarf galaxy is actually being disrupted gravitationally by us, the Milky Way, and some of the stars that are closest to us are probably being dragged toward us, and probably sometime in the next way more than millennia, I don't know what the next bigger unit is, Milky Way may actually absorb that nearest dwarf galaxy. The next major galaxy out there is Andromeda. Y'all probably don't remember the book Andromeda's Strain. It was a weird science fiction book written by a really famous author. I think Michael Crichton, I believe, is the one who wrote it. It was really bizarre back when I was in school. It's 2 million light years away. So 100,000 light years is our diameter. And multiply that by 20, and that's the next closest galaxy, major galaxy, and that's Andromeda. It's about 22 million light years away, and it's very similar to the Milky Way. So basically, a lot of what we know about how we look is by looking at that. And the pictures of that taken by the Hubble Space Telescope, pretty incredible. I think that's it right there. Oh, goodness, I've gotten behind in some of the special features. There's a nice little closer look here at extraterrestrials. What do we mean by that? Does anyone know? Extraterrestrials. That would be people from other lands, other planets, other whatever. Do y'all remember the movie E.T.? Any of you seen it? Yeah. That was supposedly the story of that one. Okay? Now, it's a great little article here, but it's talking about some things it's talking about some of the things I've mentioned before. Do any of the other stars have planets that could be similar to Earth? One of the stars with planets is only 53 light years from Earth. Okay? Are we going to receive any signals from them? If so, if they sent a signal to us, we would hear it 53 years after they sent it. So if we responded to it, that would be another 53 years. So unless they have a lot longer lifespan than we do, someone on the other end saying, what's this noise we're hearing? They would, it's sort of bizarre. Now that's one of the closest one. And then they go into other things. So it's really an interesting little blurb there on extraterrestrials. And then on the next page is Jocelyn Susan Bell Burnell. I don't know why she had so many names. She was born in 1943. I haven't heard that she died. It doesn't indicate she did. But she was the one who first found a pulsar, but then did not receive. I don't think this goes into the fact that she didn't receive a Nobel Prize for it, but her bosses did. And that's really a shame. And I can't but believe that sexism had something to do with that. Okay. We talked about the life of a star. Let's talk about the life of a galaxy. Okay? I'm trying to see. Oh, okay, this is what I'm looking for. Let's go back. The picture that you see here, I think, is Andromeda, and the one you have in your book is similar to it, but it seems like it's enhanced differently. But it looks, I think that's the same one. That gives us the best idea of what we really look like. Okay? So, before we move on, other galaxies, there is a classification scheme, and guess who's behind it? Good old Hubble. Okay, he did so much in astronomy, it's incredible. We are a spiral galaxy, okay? There are others called elliptical galaxies, which to me this looks pretty elliptical too, but it may be more roundish and less elliptical. We are a spiral galaxy. There is barred galaxy, which sort of goes out, and then there's others that you can't really classify any other ways. They call them irregular. I can't draw you pictures of those. I've never seen them, okay? I've never seen examples of it. But obviously, Hubble found enough evidence to indicate that perhaps it does have these features, okay? So, that's the classification. Let's look at the life of a galaxy. Now, I was trying to find this in the text because it does seem like the book and the slides are sort of divergent here. But I guess this is under what they just call 14.4 of the universe, which is what the whole chapter is called, the life of a galaxy. Now understand this. This is just a theory. There seems to be a fair amount of evidence to support the theory, but it's just a theory. Now, in the other course, Physical Science 112, we talk about the difference between models and theories and laws and other things. This is just a theory. The data seems, a lot of the data seems to support this idea, but a theory has to be tested. And you can't go back and test this, okay? Because it's already happened, okay? But they call it the Big Bang Theory, okay? Now, this isn't the TV show. The TV show is based on it, but don't. And actually, the TV show has a surprising amount of good science in it. But it also has so much Hollywood in it. It's hard to separate. So, here's what the idea is, that the entire universe, all these billions of billions of billions of galaxies, came out of an explosive single beginning. Now, that's pretty incredible to think about, okay? Here's the supporting evidence. First, this microwave background radiation. Okay, microwaves are they're pretty long wavelength, but they call them microwave because they're short compared to radio waves, but fairly long wavelength background radiation, and they can listen. The more they've listened deeper and deeper into the universe, it sounds like something did happen back there, but it's hard to pin down exactly what it was. Here's another piece of evidence. Large-scale expansion. Now, let me hold on just a minute. Yeah, okay, we're going to get to that. They have done enough measurements of things like other galaxies and things like we know there are many other galaxies out there besides Andromeda, and they, with powerful telescopes and stuff, have seen and measured things in them. And here's the deal. These galaxies tend to be getting further and further apart. All of them. Not just some, all of them, which means large-scale expansion. Now, that's first. That would support the idea of the big explosion and everything still is moving out. Okay. the relative abundances of elements. Now that's, yeah, okay, fine, it's there, but how could we get that many? Well, and even the very heavy elements, there's still a fair amount of those. That wouldn't tend, if you remember, it's those supernovas are the only thing that produces the things heavier than iron. We got enough of it, stuff there must have been something bigger than a supernova. So that supports this idea. Okay? Now this is more like this one. Diffuse cosmic background radiation. We have a spacecraft out there called the COBE. I've read somewhere what that stands for, but I can't remember what it is now. Spacecraft. And it seems to indicate that things are, that there was something happened a long time ago that emitted this radiation. Now, here is the most disturbing, maybe, or inexplicable thing about it. Yeah, we can tell that the galaxies are moving further apart. Part of the way you do this is what they call the redshift. Does anyone know what the Doppler effect is? Have you ever been near a train when it's coming in, or an ambulance, or anything that's emitting sound, and when it's coming toward you, sure, it's getting louder, but also the frequency's going up. Okay? But when it moves away from you, yeah, it's getting dimmer, but also the frequency is going down. Yeah, it's getting higher pitch as it comes toward you and lower pitch. That's not because they're making different noises. It's because when it's coming to you, the ambulance or the train or whatever is moving to you, but the sound is moving. Sound is a compression wave, and since the source is moving and the waves are getting closer together, increasing the frequency, moving apart, moving away from you, they're getting further apart, which lowers the frequency than what it would be if you were on the ambulance or the train itself. Okay? That's the Doppler effect. Okay? Now, the same thing happens with light. As things are moving closer together, the light rays, the waves get shorter, and therefore they go up in frequency. And when they're moving away from each other, the waves tend to get longer, and they go down in frequency. Okay? What are the longest wavelengths? Red. And things that we're noticing now are drifting toward red, and it's called the redshift. Guess who discovered this? Edwin Hubble. Okay? He's all over the place here. And because of his discovery of that, we know that they are moving further apart. Okay? Now here's the part that I was starting to say that is inexplicable in my mind. Of course, I have a very finite mind. And is almost disturbing, to think about. Not only are they moving further apart, Hubble also discovered they're accelerating the movement apart. Now, sure, if there's a Big Bang, you would expect a huge acceleration to begin with, and then it would be decreasing over time. But guess what? It's still increasing. Now, physics tells us the only way you get an acceleration is with a net force. So that means there's something out there that's accelerating this. Some force that's way bigger than we can comprehend that's going faster. Now, there is a term, and we'll talk about this in a later chapter, I think, called dark energy. And it's a really nebulous term. It's energy that's out there. We can kind of measure the effects of it. We have no clue of what's causing it and what its origin is, but it's out there. And that's the best thing they've been able to do. So the end here is the expansion going on forever, or will at some point it cease and then it really goes back, and maybe we're just one of a cycle of a bunch of big bangs and big crunches. The thing is, this thing of acceleration of the distance apart, large-scale expansion, but accelerating, that would tend to negate the idea of this unless the acceleration stops, slows down, and starts decelerating. Then maybe you could have. But right now, we're still accelerating. Now, here's a model, and this is just a model of how people have described this. That at one time, let's just say you're making raisin bread, and you wadded it up and set it aside, and you've got raisins evenly distributed throughout the dough. And then you set it on the stove top, but not baking it yet, and let it rise because there's yeast in there. Well, all the raisins, every one of them, tends to get further and further apart. That's what our universe seems to be doing, ever expanding. Okay, the galaxies are moving further apart, not just moving further apart, accelerating further apart. The accelerating part, I can't begin to guess. The moving apart, yeah, that sort of makes sense. With the Big Bang, that sort of makes sense. But accelerating, that means there's something continuing to add force or energy to the situation, forcing them further and further apart. Figure that one out, you may win a dark. Oh yeah, it's this chapter right here, Dark Energy, on page 369. A very good read. Okay? Now, this, I don't see this figure in our text anymore. This is an older one. This is sort of saying the same thing. They think the Big Bang happened somewhere back here, and then in time the galaxies were like this, moving further apart. Now they're even further apart. The thing is, they're increasing their acceleration away from each other. That's the part I can't even come up with an idea on, except maybe dark energy. Okay. Now, there's a couple more things here. We talked about some of the cosmic background, microwave background radiation. They have a pretty good figure of that in figure 1420. By making accurate measurements of the cosmic microwave background fluctuations, the WMAP, or WMAP, wasn't able to measure the density and composition of the universe, providing the best early observation of the distribution of dark matter and dark energy. Okay, even that caption is enough to confuse me. But anyway, that's mentioned. They have down here one more equation, and this is Hubble's law. There's Hubble again. In other words, he could be a paper topic himself. It could be Hubble's law, Hubble Space Telescope, they just named after him. Redshift, I mean, there's just tons of things out there that you could do. But Hubble's law allows us to estimate the speed at which things are separating, and they have a constant there, and then they have an example that you can apply that to. The galaxy NGC 7814, they don't even have names for a lot of them, approximates 50 million light years from the Milky Way, is approximately that. How fast is it moving away from us? And you can use his law to come up with that. 1,075 kilometers per second is what it comes out to. And then they have another one, and it talking about spectral lines and stuff that we haven't done. And by the way, that WMAP is Wilkinson Microwave Anisotropy probe. That's what the WMAP stands for. Well, just a few other items. The Big Bang theory, if it's true, ages the universe at about 13.7 billion years. Okay, 13.7 billion years. Okay, and other age estimating techniques agree with that. The next page, page 371, is dark matter. Now, dark energy to me is a lot fuzzier. Dark matter I can kind of get a grasp on. Okay? And when it says dark, that doesn't mean it's necessarily black. It just means it's not giving off light. And we think that most of the matter out there is in those stars and probably the solar systems around the stars, most of it in the stars. We're led more and more to think there's a lot of blackness out there that you don't see. You only see the stars because they're hot. But there's a lot of matter out there that's not hot. But if you think about these cold lumps of carbon, every star that's ever died, that's what it wound up in. Well, if it didn't end up in a black hole, a star or something. Okay? So there's a lot of that. There's a lot of masses of nebula that haven't formed into a star, or planetary nebula that have been blown away from a star. They have no temperature here to give off any light. We can sort of see them because we can see as they come in between us and some other star or something. We know they're there. Okay? So there's a lot of mass out there that we can't account for with what we see. And this blurb will tell you that there may be a lot more dark matter than there is light matter, okay, which is really sort of scary. Okay. What's that? Okay. When a star dies, when it's used up all of its energy, one of four things. Okay? And this sort of shows it. If it's a small star, it basically winds up as a bunch of mass out there, mostly carbon, because that's the last fusion that you had with it, and most of the other gases have gone out into space, so they form these nebulae again. So this is a big hot, and I mean it can be sizable, probably the size of a continent or something like that. So it's sizable as something like this. That's for the low mass stars, and the mid mass stars, that's what they all wind up being. Plus the gases that have been blown out will probably go back into heaven. The very largest of the stars either wind up as a neutron star, which is out there very, very, very massive, and probably still very hot, but also giving off that pulse. So that's how they know they're there. They may not see them as much as sense them. Or they end up in black holes. That would be the very, very, very most massive stars. And that we don't know what it is. It's just sucking everything in, and we don't know what it's doing. So that's the end. But of course, every step of the way is pulling stuff out into the thing, which goes back into the nebula. So we could have recycled stars many times over. All right. Good question, though. Now, there is another figure that's in this edition that wasn't in the earlier editions. And these are three possible outcomes for our universe. Okay? Given the universe's density, it will either begin to collapse, and that's what we saw. Goodness, I can't get to it. Yeah, the end, they call it big crunch. It collapses on itself, and then maybe rebounds and does another big bang. We don't know. We won't be around to see it. Cease expansion, but continue to expand through time. So in other words, just sort of drift, okay? Or, cease expansion, which sort of stops, or continue to expand through time. Most of the data we get now is it's accelerating and will expand indefinitely. But we don't know. We've only been collecting this data for maybe a few decades. I mean, we haven't had the science to do it until a few decades. So we're going on a very small thing. We don't know what the overall picture is. But we're, in a sense, looking back in time by all the things that are happening before. Okay. So, That does end the chapter. All right. Now, since we finished the chapter today, that means we'll have the lab for this chapter next time, because we sure don't have time enough to do it today. Which also means we'll have the test for this chapter next time. Let me give you a few hints on good things to do for the test. Number one, I'll say this every chapter, nothing replaces reading the text. That's your best way to study for it. Probably best to read it before I talk about it, and before we see the slides, but even if you don't get to do that, read it during or read it after, but read the text. Then at the end, there's a summary. It's kind of like the Reader's Digest condensed version. Okay, it really does. It's way too short, but it does hit the high points pretty well. There is also a summary of equations. Don't worry about them in this case because we haven't really done that much with formulas and equations. They're kind of based on the first 13 chapters. And since y'all haven't done those, I can't put too much on it. The key terms here are pretty good. This is sort of a short list compared to other chapters, but if you know something about either how to identify or describe or explain these key terms, you're going to be doing really well. But I think the very best thing to do is these applying the concepts. These are multiple choice questions. There's 50 of them, which is about average or maybe a little bit more than average. They're multiple choice, and there's a key at the end, answer key at the end. So do your best to try to answer them and then compare to the key. If you get any wrong, see if you can figure out why you got it wrong. If you can't figure out why you got it wrong, bring it to class. They may have made a mistake here, but the odds are there is something that you weren't taking into account. So that is the next best, I think the very best thing after you've read the chapter is to do that, applying the concepts. Now there's questions for thought, and this chapter has a full 21, which is more than most chapters do. I don't say or suggest that you do all these. I would at least read through and think through all these. Go back through the book, see if you can have a good idea what the answers are. Okay? For further analysis, there's only 5 of those. These are usually pretty good to look at too. That's probably a few fewer than normal. Then there's a invitation to inquiry, which is sort of some fun things to look at. You might think of some paper topics there. And by the way, let me go back to, remember I said that about Susan Burrell, Brown, whatever her name was. If you choose to write on her as a paper topic, this cannot be your source. Now, this may be the source of a lot of good ideas, but you have to get source outside the book. So this cannot be your source. This may give you the idea of where to look. You may see in here that Anthony Hewish is mentioned. That was her major professor, you might say. She was head of the James Clerk Maxwell. They misspelled Clark, by the way, telescopic section. You can write on him. I mean, there's a lot of things you can get from looking at this, okay, and some of the other things. Then there's the parallel exercises. Someone was asking about the small book versus the big one. I asked them to put the answers for the parallel exercises group A in the back of your book. I haven't found it yet. If they're there, I don't know where to tell you to look. When they did the customized edition, this is the second one we've had. The first one didn't include that, and I said, please put that in. I haven't found it in that one. If you found it, let me know, and we'll tell everybody. But those are worth looking at, too. A lot of them are based on those formulas and equations. Since we're not doing those, don't sweat too much about that. Okay. We've got 10 more minutes. This is what I meant to hit. I hit the right key, but it just happened to be on top of something that I didn't want it to be on top of. Okay. Let's move on and at least introduce Chapter 15. But while this is coming up, let me go through what the next. I don't want to cheat you out of a penny of your tuition dollar here, okay? You know, I want you to get the full amount. So let's look at next time, okay? We basically have 3.5 hours together, right? The last half hour, that will be from 3 to 3:30, will be the test. Before that, the next previous will be from 1 to 3. That will be the lab time. And we'll do it all as one big group, okay? Okay? That will be our lab time. So that makes 12 to 1 to be the only lecture time. So we're not going to have much time to lecture in chapter 15 next time. So I want to get a little bit of it done now. But then once we reach 1 o'clock, we will go to lab time. And then if we finish the lab in 2 hours, we'll stop, or less than 2 hours, we'll stop, and whenever you want to take your test, you can. The test probably won't take you a full 30 minutes, so whenever you're through, you can go. That's why I put the test at the very end, the lab right before that, the lecture time will be at the beginning. That way you don't have to be waiting for someone else to finish the test and we're going to go back and do lecture or lab. I do it so you get to leave as early as possible. But not today, okay? We'll get as much out of this today as we can. So let's go make the slideshow from current slide. Okay, in this chapter we're going to be talking about the solar system. We started with the universe. Now we're going to narrow down to the solar system. Now what does solar mean? Our sun. Sol. Good old Sol. And this is the system around our sun. That would be the sun, the planets, the asteroids, the meteors, everything else that's associated with us. That's our solar system. Okay? Now this happens to be a picture, I can't tell for now, but I think it's Uranus or Neptune. They are both usually blue, and there's some huge storm that's going on around that planet. I think it's probably Neptune, but I'm not sure. Okay, here's the core concept that's on that same introductory page. The solar system is comprised of the sun, that's the center of it, the orbiting planets, we're going to call that 8 for now, dwarf planets, we're going to name at least 5, but there may be a few others, and then other small solar system bodies that include the asteroids, meteors, and then several of the planets have moons around them. So those are all included in our solar system. Okay? Now, 15.1 is planets, dwarf planets, moons, and other bodies. Now notice this, the new edition says dwarf planets, the old edition just said planets, moons, and other bodies. Now there's an overall governing body, authority. The International Astronomical Union, IAU. It's the governing body, governing authority that decides what the names of these celestial bodies are. Now many of them have been named way before they formed this, so those names were adopted. But anything that's been found out since. Remember our galaxy was NSB, that was 1492. That wasn't the number either. Sometimes they don't have specific names, so they designate. So that's this one. So they decide this. They also define what's a planet and what's not. What's a dwarf planet as opposed to a planet. What the other smaller solar system bodies are or not. Now, one of the big deals for this is in 2003, the IAU took Pluto off of being a planet and made it a dwarf planet. It was redefined as a dwarf planet according to those IAU definitions. Now, what are some of those definitions? We're not going to get into these in great detail, but for instance, the size matters some, okay? Not hugely, but some, okay? And Pluto was on the lower end of that scale, okay? Another important thing was the plane of revolution. Most of the planets fall pretty close to one plane around the sun. There's a few that tilt this way, a few that way, but Pluto was like this, like 17 degrees off from the others. So that was another thing, okay? Its shape, there's several things it did, but those were two of the major ones. So Pluto was redefined as a dwarf planet, no longer a planet. Okay, we used to say back when I was growing up, Pluto was the ninth planet. And by the way, one of the earlier things when we were talking about absolute or relative or parent, goodness, I can't think of the word now. How well you can see the things. Pluto was mentioned down there, and Pluto is not visible unless you have it was below what very powerful telescopes. I mean, you have to really get something strong to see Pluto. It's way out there, folks. Oh, another one. The ellipticity of the orbit. Most of the planets, they're all ellipses. They're none of them perfectly circular, but they're not far off from being circles. Pluto, way off. Some of the time, Pluto was closer to the Sun than Neptune. Other times, it was way further. So when you would see the things, that was the average distance, because Pluto was almost acting more like a comet than it was a planet. So those are all things that the definitions. I can't get into all of them, but that's some of them. So here's what we have. The solar system is made up of the sun. And I want to read you a statement here. And I think this is very, very important, if I can just find it now. Because there's something else that shows up on the slides that sounds like it's contradicting this. But this is it. Okay, here it is. On page 379, the last paragraph on that page. The sun has 700 times the mass of all the planets, moons, minor members of the solar system put together. The sun is 700 times everything else in the solar system put together. So by far the sun is the biggest thing in our solar system. By far, 700 times bigger than everything else put together. Later you'll see a slide that says the comets, are more massive than everything else in the solar system, the sum of all the comets. Except for the sun. The sun is 700 times them and everything else put together. So don't get that wrong. Okay. Now we're down to 8 planets, approximately 100 moons. More than half of those are around Jupiter, by the way. And then a whole lot around Saturn, and quite a few around Neptune and Uranus, and very few on the others. Thousands of asteroids, millions of icy bodies, and some of those being comets and some not. So you see there's tons and tons and tons of things out there, but the sun is more than 700 times bigger, more massive than all these put together. The thing later will be talking about these icy bodies and comets, to say they're more massive than everything else in the solar system, but they're excluding. They don't say excluding the sun, but they should. Okay, I think that's all we've got time for. So we will begin next time with what's the definition of an astronomical unit. So this will be our slide right there. Okay, good deal. All right. All right, you do too. We'll see you on Thursday. I'll try not to cheat you out of any of your tuition dollar, okay?